For centuries, the periodic table has been our map of the chemical universe, neatly organizing the building blocks of matter. But what if there's more beyond the edge of that map? As technology pushes the boundaries of physics and chemistry, scientists are beginning to explore the mysterious world of synthetic elements, those born not in nature, but in powerful laboratories and particle accelerators. So, is it possible to go even further? Can we break the rules, step beyond the familiar boxes of the periodic table, and create something truly unknown? Let's dive into this mind-bending scientific frontier and explore what happens when humanity tries to outdo nature itself. The periodic table, often called the periodic table of the elements, is one of the most famous tools in all of science. It's like a big chart that arranges all the known chemical elements in a special order. The elements are placed in rows, called periods, and columns, called groups. This order isn't random. It's based on a rule called the periodic law. This law says that when elements are arranged by their atomic number, the number of protons in the nucleus of an atom, certain patterns in their properties appear again and again. This table isn't just important in chemistry. Scientists in physics and other fields also use it. It's split into 4 main blocks, each shaped like a rectangle, and the elements in the same group or column usually behave in similar ways. That's why we can predict how an element might act just by seeing where it is on the table. There are also trends that run in different directions on the table. As you move down a group, a column, elements tend to become more metallic. If you move from right to left across a period, a row, you'll also see increasing metallic character. But if you move diagonally from the bottom left corner to the top right corner, the elements become more non-metallic. These patterns help scientists understand how elements react and combine. The very first version of the periodic table that gained worldwide recognition was created by a Russian chemist named Dmitry Mendeleev in the year 1869. Back then, scientists didn't know about all the elements, so Mendeleev left blank spaces in his table. Amazingly, he used the periodic law to guess the properties of those missing elements, and he was right. His discovery was considered a major breakthrough in the late 19th century. In the early 20th century, scientists figured out more details, such as atomic numbers and quantum mechanics, which helped explain how atoms are built. In 1945, an American scientist named Glenn T. Seaborg found out that a group of elements called the actinides actually belonged in a different section of the table, called the F block, not the D block. That gave us a more modern version of the table that we still use today. Now, the periodic table is a central part of chemistry education and research. As science continues to advance, so does the periodic table. In nature, only the elements with atomic numbers from 1 to 94 are found. If scientists want to go beyond that, they have to create new elements in laboratories. By the year 2010, scientists had discovered 118 elements, which filled the first 7 rows of the table. However, the properties of the heaviest elements are still being studied to make sure they really belong where we've placed them. Scientists also think there may be even more elements out there, though we don't know exactly how many can exist. Some experts are also debating whether the layout of the current table is the best possible one. There are many ways to show the periodic law, and people are still exploring better formats for the table. Each element has a unique atomic number, written as Z, which comes from the German word Zahl, meaning number. This number tells us how many protons are in an atom's nucleus. That number makes each element special. For example, hydrogen has 1 proton and is element number 1. Helium has 2 protons and is number 2, and lithium has 3 protons and is number 3. Scientists use symbols to shorten these names: H for hydrogen, He for helium, and Li for lithium. Now, even though protons decide what element an atom is, there are also neutrons, which add weight but don't change the element's identity. Atoms of the same element can have different numbers of neutrons. These versions are called isotopes. Most elements found in nature are actually mixtures of different isotopes. Because of this, each element has an average atomic weight that reflects the mix of its natural isotopes. For example, carbon atoms all have 6 protons, but they can have 6, 7, or even 8 neutrons. Most carbon atoms have 6 neutrons, but about 1 in every 100 has 7, and only a tiny amount have 8. Isotopes are not shown separately on the periodic table. They're grouped under the same element. When atomic mass is listed, it's usually the average weight. But if an element has no stable natural isotopes, the table usually shows the weight of the most stable isotope instead. In the regular periodic table, the elements are arranged by increasing atomic number. A new row begins each time a new electron shell gets its first electron. The columns, groups, are based on how the electrons are arranged. For instance, oxygen, sulfur, and selenium are in the same group because they all have 4 electrons in their outermost p subshell. That's why elements in the same group tend to behave similarly, especially when they form chemical bonds. In some parts of the table, like the F block and D block, elements in the same row can also have similar properties. Today, scientists have discovered 118 elements. The first 94 are found naturally on Earth. The rest, from element number 95, americium, to 118, oganesson, exist only because we made them in labs. Out of the 94 natural elements, 83 have been around since Earth was formed. The remaining 11 come from the decay of those older elements. Some of the rarer elements were first made in the lab before we later discovered tiny traces of them in nature. These include technetium, element number 43, promethium, element number 61, astatine, element number 85, neptunium, element number 93, and plutonium, element number 94. No one has ever seen a visible amount of any element heavier than einsteinium, element number 99, in its pure form. Some elements, like francium, element number 87, have only ever been seen by the light they give off in microscopic amounts, as few as 300,000 atoms. Out of the 94 natural elements, 80 are stable, meaning they don't decay. One more, bismuth, is almost stable. It decays so slowly that it lasts much longer than the universe has existed. 2 others, thorium and uranium, decay very slowly over billions of years and have stuck around since Earth formed. The remaining 11 decay much faster, so they only exist today because they are constantly being created again as byproducts in the decay of thorium and uranium. All 24 man-made elements are radioactive and decay quickly. According to international rules, the vertical columns on the periodic table, called groups, are numbered using regular counting numbers from 1 to 18. This numbering starts from the far left column, which contains the alkali metals, and ends at the far right column, which holds the noble gases. The groups in the middle section, called the F block, are left out of this numbering system. Each group can also be named after the first element found in it. For example, group number 3 is sometimes called the scandium group, because scandium is the first element in that column. In the past, groups were labeled differently. They used Roman numerals instead of regular numbers. In the United States, these Roman numerals were followed by either the letter A or B. The letter A was used for elements in the S block or P block, and the letter B was used for elements in the D block. The Roman numerals generally matched the last digit of the modern numbering. For instance, what we now call group number 4 used to be called group IVB, and group number 14 was called group IVA. In Europe, they used a similar system, but with one major difference. The letters were flipped. The letter A was used for groups 1 through 7, and B was used for groups 11 through 17. Groups 8, 9, and 10 were treated as one large group, which was called Group 8 in both systems. This older system was officially replaced in the year 1988 when the International Union of Pure and Applied Chemistry, often just called IUPAC, introduced the new system using numbers 1 through 18. Since then, the old Roman numeral names have been considered outdated. Even though the naming has changed, both old and new systems describe the same periodic table. There are also different versions of how the table is arranged visually. One version includes the F block in the main body of the table, which stretches it out to a total of 32 columns. This version is often called the long form. The other version cuts out the F block and shows only 18 columns and is known as the medium long form. The 32-column version has the benefit of showing all the elements in their correct order. However, it takes up more space, so the choice between the two versions is often just a matter of convenience or preference. Both forms give the same scientific information. For example, if scientists are discussing which elements belong to group number 3, both versions of the table can be used equally and fairly. Most periodic tables at least show the chemical symbols of the elements. Many also include extra information, such as colors that represent different element groups, or data like atomic numbers and atomic weights. The example table mentioned here includes each element's name, atomic number, the type of block it belongs to, how it occurs in nature, and its standard atomic weight. For elements that are too short-lived to have a standard atomic weight, the mass number of their most stable known isotope is shown instead. Other tables might also show things like whether the element is a solid, liquid, or gas, its melting and boiling points, how dense it is, and how it fits into different classification systems. The periodic table is more than just a chart. It's a visual representation of the periodic law. This scientific rule says that the properties and inner structure of elements follow a repeating pattern based on their atomic number. The elements are placed in the table based on how their electrons are arranged, and the patterns in these arrangements explain why certain properties repeat across the table. Electrons, the tiny negatively charged particles in atoms, don't just move around randomly. They are found in specific areas called orbitals, and these orbitals describe the likelihood of finding an electron in a certain space around the atom's center. The energy levels of electrons are not continuous. They can only exist at specific levels, like steps on a staircase. Also, no two electrons in an atom can be exactly the same. This is called the Pauli exclusion principle. Electrons fill up different energy levels called shells, and each shell is divided into smaller parts called subshells, which contain the orbitals. Each orbital can hold up to 2 electrons. These 2 electrons are distinguished by something called spin, which is usually referred to as either up or down. In a stable, cold atom, meaning one that is not excited or energized, electrons always try to stay in the lowest energy orbitals they can. The electrons that are in the outermost shell, known as valence electrons, are the ones that can take part in chemical reactions. The inner ones are called core electrons, and they usually stay close to the nucleus. So far, scientists have observed elements with up to 7 electron shells. The very first shell has only one orbital, called the 1s orbital, which can hold 2 electrons. The second shell has a 2s orbital and 3 2p orbitals. That makes room for a total of 8 electrons. The third shell includes a 3s orbital, 3 3p orbitals, and 5 3d orbitals, allowing it to hold up to 18 electrons. The fourth shell has 1 4s orbital, 3 4p orbitals, 5 4d orbitals, and 7 4f orbitals, which means it can hold up to 32 electrons. Higher shells follow this same pattern, but their orbitals are not filled in any of the known elements' natural states. Each subshell and orbital is described using a set of 4 quantum numbers. These are the principal quantum number, which tells you the main energy level, the azimuthal quantum number, which tells you the shape of the orbital, the magnetic quantum number, which tells you the orientation of the orbital, and the spin quantum number, which tells you the electron's spin direction. The order in which these subshells are filled is mostly guided by something called the Aufbau principle, also known as the Madelung or Kleshkowski rule. This rule was first noticed by a scientist named Erwin Madelung. and was later explained in more detail by Vsevolod Kleshkovsky and others. Thanks to this rule, we can build up the periodic table by adding one electron at a time, starting from the simplest atom, hydrogen. Hydrogen has only one electron, and it goes into the lowest energy orbital, which is the 1s orbital. Its electron configuration is written as 1s1. The next element, helium, adds a second electron to that same orbital, making it 1s2 and completing the first shell. When we reach the third element in the periodic table, lithium, something important happens in the structure of the atom. The very first shell, which can only hold 2 electrons, is now completely full. So lithium's third electron has to go into a new, higher energy shell, the second shell. It settles into what's called a 2s orbital, which is just a region of space where an electron is likely to be found. This gives lithium the electron configuration 1s2, 2s1. In other words, 2 electrons in the 1s subshell and 1 electron in the 2s subshell. That single electron in the 2s subshell is lithium's only valence electron, the one that can take part in chemical reactions. The other 2 electrons, sitting snugly in the 1s shell, are held so tightly to the nucleus that they don't usually get involved in bonding. Because of this, we call the 1s subshell a core shell. And from lithium onward, the 1s subshell remains a core shell for all elements. The next element, beryllium, brings in 1 more electron, which also goes into the 2s subshell. Now that shell is full too, giving beryllium the configuration 1s2, 2s2. Next, the second shell continues filling, but this time with electrons entering the 2p orbitals. Boron adds 1 electron to the 2p subshell, 1s2, 2s2, 2p1. Carbon adds another, 2p2, and nitrogen brings it to 3, 2p3. By this point, each of the 3 2p orbitals has 1 electron. This follows Hund's rule, which tells us that electrons prefer to stay separate in different orbitals of the same type before pairing up. After nitrogen comes oxygen, which adds a second electron into one of those 2p orbitals. Now it's 2p4. Then comes fluorine, 2p5, and finally neon, which completes the second shell with a total of 8 outer electrons, 2p6. At this stage, the second shell is full, just like the first shell was for helium. Now let's move to element number 11, sodium. With the first and second shells completely filled, the third shell starts to receive electrons. Sodium's new electron goes into the 3s subshell, making its configuration 1s2, 2s2, 2p6, 3s1. For simplicity, scientists often write this as 3s1, which means it has the same inner structure as neon, plus 1 more electron in the third shell. Next comes magnesium, which adds another electron to the 3s orbital, making it full. After magnesium, the elements aluminum, silicon, phosphorus, sulfur, chlorine, and argon add electrons to the 3p orbitals, filling them one by one until argon finishes the third shell completely. This series of elements, from sodium to argon, closely mirrors the pattern we saw from lithium to neon. That repeating pattern is what gives the periodic table its special shape and name. As we move through the table, the properties of elements repeat at regular, though not always perfectly consistent, intervals. This is the heart of what's called periodicity. The first 18 elements, from hydrogen to argon, form the beginning of the periodic table. Elements that fall into the same column are grouped together because they have the same number of valence electrons. That means they tend to behave similarly in chemical reactions. These columns are known as groups. There is one small exception to this pattern: helium. Even though helium has only 2 electrons, just like beryllium and magnesium, it is usually placed with neon and argon because its outer shell is also completely full. This section of the periodic table has 8 columns, which match the maximum of 8 electrons that can fit in an outer shell. A new row, or period, starts whenever a new shell begins to fill with electrons. The table is also color-coded in blocks. Elements in the s block, colored red, are filling s orbitals, and those in the p block, colored yellow, are filling p orbitals. As we begin the next period, elements like potassium and calcium start filling the 4th shell. Potassium adds 1 electron to the 4s subshell, 4s1, and calcium adds another, completing it, 4s2. But after calcium, things get a little more complicated. Scandium begins to fill the 3d subshell, even though we're in the 4th shell now. This is because the energy levels of the 4s and 3d orbitals are very close, so electrons can go into either depending on small changes in the atom's environment. For example, chromium does something unexpected. Instead of filling the 3d orbital with 4 electrons and having 2 in the 4s, it shifts things around to end up with 5 in the 3d and only 1 in the 4s, 3d 5 4s1. The same kind of thing happens with copper, which ends up with 10 electrons in the 3d and just 1 in the 4s. These exceptions are known as violations of the Madelung rule. Even though these little quirks happen, they usually don't matter much in chemistry. Most chemical reactions don't involve isolated atoms floating in space. They happen in environments where nearby atoms can influence energy levels. Because of that, the periodic table sticks to ideal patterns and doesn't focus too much on these exceptions. Once we reach zinc, the 3d orbitals are completely full, 10 electrons. After that, the 4p orbitals begin to fill, 1 electron at a time, from gallium through krypton. From gallium onward, the 3d electrons become part of the atom's core and no longer participate in reactions. The elements that fill s and p orbitals in their outermost shells are called main group elements. The ones that fill d orbitals, which are deeper inside the atom, are called transition elements, or transition metals, since they are all metallic. The next row of the table continues the pattern. Rubidium and strontium fill the 5s orbitals, followed by 10 elements that fill the 4d orbitals, from yttrium to cadmium, and then 6 more that fill the 5p orbitals, from indium to xenon. From indium onward, the 4d orbitals become part of the core. The 6th row begins with 2 more s-block elements, cesium and barium. After that, things get even more interesting as the f-block begins. These are the inner transition elements, starting with lanthanum. Now there are 3 types of subshells at very similar energy levels: 4f, 5d, and 6s. That means they compete for electrons, and the order of filling becomes irregular again. Although lanthanum itself doesn't fill the 4f orbital, its energy level is low enough that it still participates in bonding. That's why most scientists agree the f block starts here. At ytterbium, all 7 4f orbitals are full, 14 electrons. After that, we go through 10 more transition metals, lutetium to mercury, and finally 6 more main group elements, thallium to radon, complete the row. From lutetium onward, the 4f orbitals are part of the core, and from thallium onward, the 5d orbitals are too. The 7th row of the periodic table works in a similar way to the 6th row. First, the 7s orbital fills up with francium and radium. After that, the 5f orbital fills with elements from actinium to nobelium. Then comes the 6d orbital, which includes lawrencium to copernicium, and finally, the 7p orbital, which has elements from nihonium to oganesson. Starting with lawrencium, the 5f orbitals are considered part of the inner core of the atom, meaning they're no longer involved in chemical reactions. It's also believed that beginning with nihonium, the 6d orbitals start to behave the same way, becoming part of the core and not affecting chemical behavior. But as always, the periodic table isn't without its surprises. There are some exceptions to the expected filling order. For example, as individual atoms, actinium and thorium don't actually fill the 5f orbital, and lawrencium doesn't fill the 6d orbital. Still, in real chemical environments, these orbitals can end up being filled anyway. This shows that chemistry in the real world can be a bit more flexible than the neat rules of textbooks. For a very long time, the 7th row of the periodic table wasn't complete. That's because many of its elements don't exist naturally on Earth. Scientists had to create them in laboratories. This process began in 1940, when neptunium was made. In fact, the very first element ever made in a lab instead of being found in nature was technetium, back in 1937. The row was finally completed when tennessine was created in 2010. The last element on the row, oganesson, had actually already been made earlier, in 2002. All the unnamed elements in this row were finally given official names in 2016. A table exists that shows the electron configurations for atoms of each element in their neutral, gas-like state. However, keep in mind that in different chemical environments, atoms might prefer slightly different configurations. The main group elements, those in the tall columns, generally follow simple and regular rules for electron filling. But the transition metals and inner transition metals, like the lanthanides and actinides, show about 20 exceptions. These happen because some subshells are very close in energy, so electrons can sometimes jump around in unexpected ways. For the last 10 elements, from element number 109 to 118, we don't have enough experimental data yet. So scientists have used theoretical calculations to guess their electron configurations. In electron configuration charts, completely filled subshells are often shaded in gray, so it's easier to focus on the electrons that actually take part in chemical reactions. Even though today's periodic table is used around the world, there's still one big debate going on. Where exactly should hydrogen and helium be placed? Based on their electron configurations, hydrogen has 1 electron in its outer shell and helium has 2. Hydrogen fits in group 1 and helium fits in group 2. And while hydrogen is usually shown in group 1, helium is almost always placed in group 18 with the noble gases. Why the debate? It's because some scientists believe that chemical behavior should decide where elements go, while others think electronic structure is more important. Hydrogen acts like a group 1 metal in some ways. It has just 1 electron and often loses it in chemical reactions. It can even push metals out of their salts, just like a metal would. But hydrogen is a non-metallic gas under normal conditions, very different from the solid, reactive metals in group 1. Hydrogen can also behave like a halogen, group 17, especially when it gains an electron to form hydrides, much like how fluorine or chlorine do. Interestingly, hydrogen, fluorine, and chlorine are all gases at room temperature. But hydrogen doesn't fit perfectly into either group. It doesn't strongly give or take electrons, and it doesn't react with water like group 1 metals do. Because of this mix of behaviors, hydrogen is hard to place. While it's usually found in group 1, other versions of the periodic table put it in group 17, in both groups, or even floating on its own above all groups. However, some scientists, like Eric Seri, criticize this floating position. He says it makes hydrogen seem like it doesn't belong to the periodic law, which applies to all elements. Now let's talk about helium. It's a bit of an oddball too. Although it has 2 electrons, like the group 2 elements, it behaves more like the noble gases in group 18. It's inert, meaning it doesn't react under normal conditions, and it has a full outer shell. So even though helium's electron structure suggests it belongs in group 2, its chemical behavior is much more like the noble gases. That's why, in 1988, the official international chemistry body IUPAC rejected the idea of moving helium to group 2. Still, some scientists continue to argue that helium does share traits with the group 2 elements. For example, solid helium forms the same kind of crystal structure, hexagonal, close-packed, as beryllium and magnesium, which are both in group 2, And recently, researchers have predicted that helium might form unusual compounds like GeO-LiF2, which are similar to compounds formed by beryllium. This wouldn't be expected for other noble gases like neon, supporting the idea that helium is a bit different from its Group 18 neighbors. There's also a scientific argument based on orbital sizes. The first orbital in any block, like the first s orbital for hydrogen and helium, is unusually small. This leads to first-row anomalies, where the first element in a group behaves very differently from the others. Helium shows this anomaly only if it's placed in Group 2, not in Group 18. Some scientists say the relationship between helium and beryllium is like the one between hydrogen and lithium, and hydrogen and lithium are usually shown in the same group. For instance, there's a big jump in atomic size between helium and beryllium, and between neon and argon, but not between helium and neon, which suggests helium might belong with beryllium instead. This size trend also shows up in boiling points and how well gases dissolve in water. Again, helium is more like grouping two elements in this way. Still, almost all periodic tables place helium in Group 18 because of its extreme non-reactiveness, which is typical of the noble gases. Rarely, you might see a table that shows both hydrogen and helium floating above the other elements, not belonging to any group, but this is uncommon. In many versions of the periodic table, there's a shift in how the F block is shown. Instead of starting with lanthanum and actinium, these two elements are moved into the D block, specifically into Group 3. Then, the F block begins with cerium and thorium and ends with lutetium and lawrencium. This setup makes the D block look very uneven. It's like it's been chopped in half. This design goes back to old mistakes scientists made when they were first figuring out how electrons are arranged in atoms. Today, with much better tools and knowledge, scientists now mostly agree that the table makes more sense if lutetium and lawrencium are in Group 3, and if the F block starts with lanthanum and ends with nobelium. In the year 1948, two famous physicists, Lev Landau and Evgeny Lifshitz, noticed something interesting. By the time you reach the element ytterbium, the 4F shell is completely filled with electrons. Because of this, they thought it was wrong to include lutetium in the F block at all. They didn't go as far as moving lanthanum out of the D block, but that idea came a bit later. In 1963, another scientist, Jun Kondo, discovered that lanthanum becomes a superconductor at very low temperatures, which meant that its 4F electrons could play a role in its behavior. Then, in 1965, David C. Hamilton connected this idea to lanthanum's place on the periodic table. He argued that the F block should actually include all the elements from lanthanum to ytterbium and from actinium to nobelium. Since then, lots of scientific evidence, physical, chemical, and electronic, has supported this idea. In 1982, the topic gained more attention thanks to William B. Jensen. Then, in 1988, and again in 2021, the International Union of Pure and Applied Chemistry, IUPAC, the global authority on chemical naming and organization, supported putting lutetium and lawrencium in Group 3. Still, many textbooks haven't updated their tables simply because many authors don't know about these changes. There's even a third version of the periodic table that sometimes shows up. In this one, the spots below yttrium in Group 3 are left blank. This kind of table, which even appears on IUPAC's own website, causes a problem. It stretches the F block to include 15 elements, from lanthanum to lutetium, and from actinium to lawrencium, even though the F orbital can only hold 14 electrons. This setup doesn't agree with how quantum mechanics works. Plus, there's often confusion in books and articles about which elements are actually in Group 3 when this version is used. Interestingly, in 2021, IUPAC admitted that this 15-element F-block idea is sometimes used by scientists studying extremely heavy elements, super heavy elements, in fact, using a very specialized branch of quantum physics. But IUPAC said this shouldn't change how the periodic table is shown to most scientists and students. Some researchers who study super-heavy elements also clarified that the 15th element in the F block is really just a placeholder for the first spot in the D block, meaning lutetium and lawrencium are still considered D block elements. Whenever the table is expanded to 32 columns, which shows all blocks clearly, IUPAC places lutetium and lawrencium directly under yttrium in group 3, confirming their place in the D block. Some scientists still argue in favor of a different setup, placing scandium, yttrium, lanthanum, and actinium in group 3. But these arguments often don't hold up logically. For example, some say lanthanum and actinium shouldn't be F block elements because they don't start filling their F orbitals when they are isolated gas phase atoms. But thorium is in the same situation, and no one argues about it being an F block element. Even more importantly, this argument misses the bigger picture. The F orbitals are actually completed at ytterbium and nobelium, which fits better with the idea of putting lutetium and lawrencium in group 3. In other words, the SCY-Lu-LR version fits the actual electron patterns better than the CY-Le-AC version. Also, these unusual electron arrangements are pretty rare and aren't usually considered when deciding where to place elements. For instance, in gas phase atoms, the D shells finish filling at copper, palladium, and gold, but chemists agree that the D block ends at zinc, cadmium, and mercury, based on a well-known pattern called the Madelung rule. What really matters is how elements behave in chemical reactions. Lanthanum and actinium, just like thorium, can use their F orbitals in chemical environments. But lutetium and lawrencium cannot. Their F orbitals are buried deep inside and don't participate in bonding or reactions. So, while yttrium and lanthanum may have the same number of valence, outer electrons, their electron shells are different. In contrast, yttrium and lutetium not only have the same number of valence electrons, but they also use the same type of orbitals. This makes their chemical behavior much more alike. Since chemical reactions involve outer electrons, elements with similar outer electron arrangements tend to act in similar ways. They often form compounds with similar patterns and proportions. That's why we put similar elements in the same column or group on the periodic table. These repeating patterns in behavior give the periodic table its name and are the foundation of what we call the periodic law. Scientists actually noticed these repeating behaviors long before they understood why they happen. Back in the early 20th century, no one really knew how big atoms were. The first serious guess came in the year 1910, when physicist Arthur Haas estimated the size of a hydrogen atom. He got surprisingly close, within a factor of 10, using a version of J.J. Thomson's old plum pudding model of the atom. An atom's size mostly depends on the size of its outermost electron orbitals. As you move across a row in the main part of the table, the atoms get smaller because the nucleus gets stronger and pulls the electrons in more tightly. But as you move down a column, atoms get larger because the outer electrons are farther from the nucleus. Interestingly, the first element in each block, like hydrogen in the S block or scandium in the D block, is unusually small. This is due to something called primogenic repulsion or kinosymmetry. It happens because these early orbitals don't have any earlier, similar orbitals to push against them. For example, the 2p orbital doesn't feel much repulsion from the 1s and 2s orbitals, so it stays small. But the 3p orbital feels strong repulsion from the 2p orbital, which forces it to expand. This pattern creates big differences between elements in the second row, which are small and love to form multiple bonds, and those in the third row and beyond, which are larger and don't bond the same way. The same kind of strange behavior also shows up in the first elements of the 1s, 2p, 3d, and 4f blocks, and even in the imaginary 5g block that hasn't been filled yet. These size differences are most extreme in the S block, less so in the P block, and even milder in the D and F blocks. In the group of elements known as the transition metals, something interesting happens. While the electrons are being added to an inner shell of the atom, the size of the atom is still mostly determined by the outermost electrons. As you move across the transition metals in the periodic table, the positive charge of the nucleus increases because more protons are being added. At the same time, extra electrons are also being added to the inner shells, and these electrons help to shield or block the pull of the nucleus from reaching the outermost electrons. These two effects, more nuclear pull and more shielding, almost cancel each other out. Because of that, the size of the atoms only gets a little smaller from left to right across the transition series. Now, some elements like those in the 4th p block and the 5th d block are smaller than we would expect. This happens because the newly added inner layers of electrons, like those in the 3rd d block or 4th f block, don't do a very good job of shielding the outer electrons from the nucleus. As a result, the nucleus pulls the outer electrons closer in. This is why, for instance, gallium atoms are slightly smaller than aluminum atoms, even though gallium comes later in the periodic table. This pattern, combined with a concept called kenosymmetry, creates a curious zigzag trend between elements in even-numbered periods and those in odd-numbered periods. This is often called secondary periodicity. Elements in even periods tend to have smaller atomic sizes and usually lose fewer electrons, while elements in odd periods tend to do the opposite, except for those in the s block. For example, in group 15 of the periodic table, phosphorus and antimony from odd periods often reach the +5 oxidation state, while nitrogen, arsenic, and bismuth from even periods are more comfortable staying at +3. A similar pattern appears in the d block. Atoms like lutetium through tungsten from period 6 are a bit smaller than their counterparts like yttrium through molybdenum from period 5. When we look at heavier elements, another fascinating effect comes into play: the laws of special relativity. Once atomic nuclei become highly charged, meaning they have lots of protons, they start affecting their electrons in strange ways. This is because the electrons move so fast that their mass actually increases and their behavior changes. These relativistic effects make heavy elements behave very differently from their lighter cousins. For instance, this is why gold has its shiny yellow color and why mercury is a liquid at room temperature. As a result of these effects, the atoms of thallium and lead from period 6 are about the same size as indium and tin from period 5, but from bismuth to radon, the 6th period p block atoms are actually larger than the 5th period ones. This happens because relativity causes the p orbitals to split. One orbital becomes smaller and more stable, while the other two expand and become less stable. That's why thallium and lead fill the smaller, stable orbitals, and bismuth through radon fill the larger, unstable ones. These unusual relativistic effects are expected to become even stronger in the very heaviest elements, especially in the 7th period of the periodic table. Scientists think that this might eventually lead to the collapse of some of the normal patterns we see in the periodic table. So far, scientists have clearly figured out the electron configurations only up to element number 108, hassium. Chemistry experiments have only been done on a few of the super-heavy elements, specifically elements number 112, carbonicium, through 115, moscovium. Learning more about these ultra-heavy elements is still an ongoing adventure in modern science. The same shrinking trend seen in atomic sizes from left to right is also seen in the sizes of ions, atoms that have gained or lost electrons. But it's a bit harder to measure because neighboring elements usually form ions with different charges. Still, when different ions have the same number of electrons, their sizes shrink as the nuclear charge increases. For example, ions in the series selenide 2-, bromide 1-, rubidium 1+, strontium 2+, yttrium 3+, zirconium 4+, niobium 5+, molybdenum 6+, and technetium 7+, all get smaller as you go along, because the nucleus pulls harder on the same number of electrons. Also, if an atom keeps losing more and more electrons, its size shrinks even more. This is because the attraction from the positively charged nucleus starts to overpower the repulsion between the remaining electrons. Another important concept is ionization energy, the amount of energy needed to remove an electron from an atom. The closer an electron is to the nucleus, the harder it is to remove, so ionization energy generally increases as you move from left to right across a period and from the bottom to the top of the periodic table. That's why ionization energy is lowest for the first element in each period, like hydrogen and the alkali metals, and highest for the noble gases at the far right. Some elements, like oxygen, break this trend a little because of how their electrons are paired, making it a bit easier to remove one. In the transition metals, even though electrons are being added to inner shells, the ones in the outer shell are still the first to go during reactions. For example, in the third d block series, the 4s electrons are usually lost before the 3d ones. The growing number of 3d electrons helps to cancel out the increasing pull of the nucleus, which is why the ionization energies don't change very much across the transition metals, though there is a small upward trend toward the end. Since metals usually lose electrons in reactions, ionization energy is often connected to how reactive they are, although other factors also play a role. Now, the opposite of ionization energy is electron affinity. That's the amount of energy released when an atom gains an electron. If an atom has a strong pull from its nucleus and an available spot in its outer shell, it will more readily accept an extra electron. So electron affinity tends to rise as you move up and to the right on the periodic table. However, noble gases are an exception. They already have full outer shells and have no room for extra electrons. That's why the halogens, just one column to the left of the noble gases, have the highest electron affinities. Some atoms, like the noble gases, don't accept extra electrons at all in the gas phase. They can only do so briefly under extreme conditions, and even then, they quickly lose the extra electron again. For instance, the most stable form of a helium anion lasts only about 359 microseconds. Because they don't want to gain or lose electrons, noble gases are usually very unreactive. Still, there are some exceptions. For instance, oxygen and fluorine have lower electron affinities than sulfur and chlorine, even though they are in the same groups. That's because oxygen and fluorine are smaller atoms, and any new electron would feel a strong repulsion from the electrons already there. In general, for nonmetals, electron affinity is linked to how reactive they are, but it's not a perfect connection. Fluorine, for example, is more reactive than chlorine, even though it has a slightly lower electron affinity. The idea of valence, how many bonds an atom can form, can be explained in two main ways. One is by counting how many hydrogen atoms can bond with it to make a simple compound. The other is by counting twice the number of oxygen atoms it can bond with to form simple oxides, not including more complex ones like peroxides. For elements in the main part of the periodic table, valence is often tied directly to the group number. Today, the concept of valence has been broadened into something called oxidation state, which is the charge an atom would have if we imagined all the other atoms in the compound as ions. Electron configurations help explain valence too. As you go across the periodic table, the number of electrons in the outermost shell increases. This number resets whenever you enter a new section of the table. For example, in period 6, cesium and barium have 1 or 2 valence electrons. Lanthanum through ytterbium have 3 to 16. Lutetium through mercury have 3 to 12, and thallium through radon have 3 to 8. However, for some elements, especially those toward the end of the D block and F block, it's not possible for them to use all their valence electrons at once in reactions. The same is true for oxygen, fluorine, and the lighter noble gases up to krypton. To fully understand this, scientists have to consider the energy changes that happen when different types of compounds form. In heavier p-block elements, The most common oxidation states tend to change by 2 steps at a time. That's because losing an extra electron exposes a deeper, more stable shell, making the ions smaller and more stable. For example, thallium loses 2 electrons to expose the 6s shell, and then often loses a third to expose the 5d shell. This trend also helps explain why group 14 has such a mix of elements. Carbon is a non-metal, silicon and germanium are semiconductors, and tin and lead are metals, but they all have 4 valence electrons. This often leads to shared oxidation states. For instance, sulfur and selenium in group 16 can both reach a maximum oxidation state of +6 and a minimum of -2. But not always. Oxygen, although in the same group, does not reach the +6 state. One of the most important characteristics of chemical elements is something called electronegativity. This is a fancy word that describes how strongly an atom pulls on shared electrons when it forms a bond with another atom. You see, atoms can bond with each other by sharing electrons. These shared electrons are usually in pairs, and they help to hold the atoms together. When 2 atoms share electrons like this, it's called a covalent bond. But the way the electrons are shared isn't always equal. Some atoms pull on the shared electrons more than others. This pulling power depends on the atom's electronegativity, which is basically how much the atom wants the electrons. If one atom has high electronegativity, it will pull the shared electrons closer to itself. If the other atom has low electronegativity, or is more electropositive, it won't pull as hard. In extreme situations, the electron doesn't just stay shared, it practically moves all the way to the more electronegative atom. When this happens, one atom gives up an electron and becomes positively charged, while the other one takes the electron and becomes negatively charged. These opposite charges attract each other, forming a different kind of bond called an ionic bond. Electronegativity depends on how strongly an atom's nucleus, the center of the atom where the protons are, can pull on electrons. Just like other atomic properties, electronegativity follows a pattern on the periodic table. As you go from the top to the bottom of a column, electronegativity usually decreases. But as you move from left to right across a row, it usually increases. The elements known as alkali metals and alkaline earth metals, like sodium or calcium, are some of the most electropositive. They don't hold on to electrons very tightly. On the other hand, elements like oxygen, fluorine, and chlorine, found in the chalcogen and halogen groups, as well as noble gases like neon and argon, are very electronegative and pull strongly on electrons. Scientists usually measure electronegativity using something called the Pauling scale. On this scale, fluorine, the most electronegative reactive element, is given a value of 4.0. Cesium, which is one of the least electronegative elements, has a value of 0.79. Interestingly, the element neon is actually the most electronegative of all, but we can't measure it on the Pauling scale because it doesn't form covalent bonds easily with other elements. An atom's electronegativity can also change depending on what it's bonded to and how many electrons it has already lost. For example, lead atoms in the +2 oxidation state have an electronegativity of about 1.87, but in the +4 state, it increases to about 2.33. Now let's talk about simple substances. These are materials made of atoms from only one chemical element. If the atoms are very electronegative, they usually form covalent bonds by sharing electrons. Depending on how they bond, they can create small molecules, like hydrogen or oxygen, which form pairs of atoms, or large, endless structures, like the crystal networks formed by carbon or silicon. Noble gases are a bit different. They don't need to bond at all because they already have a full outer shell of electrons, so they usually stay as single atoms. Substances made of separate molecules or single atoms are held together by weak forces called London dispersion forces. These forces happen because electrons inside the molecules are always moving. Sometimes they create tiny, temporary imbalances in electric charge. These little blips can influence nearby molecules, causing the electrons to move in a sort of synchronized way across a group of molecules. On the other hand, atoms that are more electropositive usually don't share electrons. They prefer to lose them. When they do, they leave behind positively charged ions, or cations. These ions sit in a sea of free-moving electrons. This sea of electrons surrounds all the ions and holds everything together. This kind of bonding is called a metallic bond, and it's what gives metals their unique properties, like being good at conducting electricity and heat. Most elements that form these kinds of bonds are called metals, while those that don't are called nonmetals. Some elements can even form different versions of simple substances with completely different structures. These versions are known as allotropes. For example, carbon can exist as both diamond and graphite, same element but totally different forms. Now let's look at what makes an element metallic. When atoms bond, either through metallic or covalent bonds, their outermost electron orbitals overlap. This overlapping creates two types of molecular orbitals: bonding orbitals, which help hold atoms together, and anti-bonding orbitals, which work against bonding. If more electrons go into bonding orbitals than anti-bonding ones, you get a strong bond. Metallic bonding happens best when each atom shares only a few electrons, and there aren't enough electrons to fill all the bonding and anti-bonding orbitals. This is the case for elements in groups 1 through 13 on the periodic table. These elements don't have enough valence electrons to build strong covalent networks, so they end up forming metallic structures instead. There are some exceptions, though, like hydrogen and boron. These two elements have such high ionization energy that they don't easily give up electrons. So hydrogen forms a molecule with 2 atoms, and boron forms a complex network of 12 atom clusters called icosahedra. In metals, the energy levels of bonding and anti-bonding orbitals are so close that they blend into a single band. Electrons can move freely through this band, which is why metals conduct electricity so well. Things start to change in group 14. Here, both covalent and metallic bonding are possible. Take carbon, for example. In diamond form, each carbon atom forms strong covalent bonds with 4 neighbors. Because the atoms are small and the bonds are tight, the energy difference between bonding and anti-bonding orbitals is huge. This means no electrons can move freely, so diamond doesn't conduct electricity. It's a non-metal. As you go down the group to bigger atoms like silicon and germanium, the bonds get weaker and the energy gap, called the band gap, becomes smaller. That's why silicon and germanium are semiconductors. At room temperature, some electrons get enough energy to jump across the band gap and carry electricity. Boron is a semiconductor too. When you get to tin and lead, the band gap disappears altogether, and these elements become metals. Interestingly, the way a material conducts electricity changes with temperature. In metals, conductivity gets worse as temperature goes up, because the atoms jiggle more and make it harder for electrons to move. In nonmetals, the opposite happens. Conductivity gets better with heat, because more electrons can jump across the band gap. That's one way scientists tell the difference between metals and nonmetals, by watching how they behave when things heat up. Elements in groups 15 through 17 have too many electrons to form large covalent molecules that extend in all directions. For the lighter elements, the bonds in small molecules with 2 atoms are so strong that they don't easily form solid phases. This is why nitrogen, oxygen, white phosphorus, yellow arsenic, sulfur, red selenium, and the halogens like fluorine, chlorine, bromine, and iodine usually exist as small covalent molecules with just a few atoms. However, the heavier elements in these groups tend to form long chains, like red phosphorus, grey selenium, and tellurium, or layered structures like graphite, carbon, black phosphorus, grey arsenic, antimony, and bismuth. These structures only stretch in 1 or 2 directions, not 3. These different forms are called allotropes, And while both types can exist in elements like phosphorus, arsenic, and selenium, the long-chained ones are more stable overall. These structures don't use all of their electron orbitals for bonding, so the atoms end up in different energy states: bonding, non-bonding, and anti-bonding. As with elements from group 14, the energy gap between these states shrinks as the atoms get heavier, allowing electrons to move more freely between the chains or layers. For example, black phosphorus, black arsenic, gray selenium, and tellurium act as semiconductors, while gray arsenic, antimony, and bismuth are semimetals. Polonium and possibly astatine are metals. As for the noble gases in group 18, they remain as individual atoms without any covalent bonding. The line that separates metals from nonmetals is roughly diagonal from the top left to the bottom right of the periodic table. The transition metals, which have many available electron orbitals to overlap, are to the left of this line. This trend makes sense since metallic behavior is linked to an element's ability to lose electrons. The further left and down you go on the periodic table, the more likely an element is to behave like a metal, and metals are far more common than nonmetals. The elements near this dividing line are harder to classify because they show characteristics of both metals and nonmetals. These elements are called semimetals or metalloids. It's important to note that the term semimetal in chemistry is not the same as in physics, which deals with the material's behavior in terms of electronic band structure. For example, bismuth is physically a semimetal, but chemists consider it a metal. The following table compares the most stable forms of elements under normal conditions. Elements shown in yellow form simple substances held together by metallic bonding. Those in light blue form giant covalent networks, while those in dark blue are made of small molecules held by weaker forces, like van der Waals forces. The noble gases are shown in violet, as their atoms exist individually and don't bond covalently. Elements that haven't been studied enough to determine their stable form are shaded gray. According to current research, these elements would likely become metals if they could form condensed phases, except for oganesson. Metals are typically shiny and dense. They have high melting and boiling points because their metallic bonds are strong, and they can be stretched or shaped without breaking because their atoms can slide past each other. Metals also conduct electricity as their electrons are free to move in all directions, and they can conduct heat by transferring energy through fast-moving electrons. These properties also exist when metals are liquid, although the atomic structure weakens slightly when they melt. Metals are usually reactive with nonmetals, though there are exceptions. For example, beryllium, chromium, manganese, antimony, bismuth, and uranium are brittle, while chromium is particularly hard. Some metals, like gallium, rubidium, cesium, and mercury, are liquids at room temperature. Gold, a noble metal, is chemically very stable. Non-metals behave differently. Some form giant covalent crystals with high melting and boiling points, while others form smaller molecules held by weak forces, so they usually have lower melting and boiling points and exist as liquids or gases at room temperature. Non-metals are usually dull and tend to react with metals, except for the noble gases, which are mostly unreactive. When non-metals are solid, they are brittle because their atoms are tightly held in place. Non-metals are less dense and don't conduct electricity well because their atoms don't have free-moving electrons. Elements close to the dividing line between metals and nonmetals have small band gaps, making them semiconductors, such as silicon, germanium, and tellurium. Selenium and arsenic both have allotropes that are semiconducting or insulating, and these properties influence how they behave. For example, selenium's gray form conducts electricity, while its red form does not. It's common to group elements that straddle the boundary between metals and nonmetals as metalloids. These elements often have properties of both, but there is no universal agreement on which elements belong to this group. Generally, silicon, germanium, arsenic, and tellurium are considered metalloids, along with boron and antimony in most sources. However, some researchers believe that antimony should be classified as a metal instead of a metalloid because of its metallic conductivity and similarities to bismuth and other p-block metals. Similarly, selenium has semiconducting properties and might also be considered a metalloid, though this is not always the case. In some cases, phosphorus is included among metalloids, but it is much rarer. There are various relationships between elements in the periodic table that don't fall within the same group. For example, some elements that are next to each other diagonally, like lithium and magnesium, share certain characteristics. Also, elements from the main groups can sometimes resemble those from the transition metal groups, or elements from the early actinides may resemble early transition metals. This is especially true when these elements have the same number of valence electrons. For instance, uranium has a similar structure to chromium and tungsten, which belong to group 6, because they all have 6 valence electrons. There are other types of relationships based on the number of valence electrons, but with different valence orbitals. These are called secondary or isodonor relationships. Elements with these relationships often have the same maximum oxidation state, but different minimum oxidation states. There are also tertiary or iso-acceptor relationships. These occur between elements with the same number of valence vacancies but different numbers of valence electrons. These elements tend to have similar minimum oxidation states but not the same maximum oxidation states. In addition to these relationships, many other physical properties of elements change in a regular way in line with the periodic law. These properties include melting points, boiling points, heats of fusion and vaporization, and atomization energy. Similar changes can also be seen in the compounds formed by these elements, such as hydrides, oxides, sulfides, and halides. While chemical properties are harder to measure precisely, they too follow a periodic pattern. For example, the acidic and basic properties of elements and their compounds, the stability of their compounds, and the ways they are isolated all exhibit periodic trends. This periodicity is widely used to predict the properties of unknown elements and compounds, and it's a key part of modern chemistry. Scientists use various names to describe sets of elements that behave similarly. The names alkali metals, alkaline earth metals, trial, tetral, pnictogen, chalcogen, halogen, and noble gas are officially recognized by the International Union of Pure and Applied Chemistry, IUPAC. Other groups can be referred to by their group number or by the name of the first element in the group. For example, Group 6 is often called the chromium group. There is some disagreement about how to classify elements. For instance, the p-block elements from groups 13 to 16 are sometimes divided based on their metallic properties. But there is no universal agreement on which elements should be considered metals, non-metals, or semi-metals, also called metalloids. Similarly, there is no clear consensus about what to call the metals after the transition metals, with terms like post-transition metals and poor metals being used. Some researchers exclude the elements of group 12 from the transition metals because they have different chemical properties, but this isn't always agreed upon, and IUPAC doesn't officially support this view. The lanthanides, or rare earth elements, are the elements from lanthanum to lutetium, which are very similar to each other. Historically, only the elements from cerium to lutetium were considered lanthanides, but lanthanum was later included by common usage. The rare earth elements also include scandium and yttrium. Similarly, the actinides are the elements from actinium to lawrencium. These elements were once thought to only include thorium to lawrencium, but this has changed over time. The properties of actinides vary more than those of the lanthanides. IUPAC prefers to use the terms lanthanoids and actinoids to avoid confusion, since the "ide" suffix typically refers to a negative ion, but lanthanides and actinides are still commonly used. As scientists have come to recognize lutetium and lawrencium as D-block elements, some have redefined the lanthanides to include only elements from lanthanum to ytterbium and the actinides from actinium to nobelium. The superheavy elements, or transactinides, are those that come after the actinides, starting from lawrencium or rutherfordium, depending on where the actinides are considered to end. These elements are short-lived and not found in nature. There are many other ways to categorize elements, depending on the field of study. For example, in astrophysics, a metal is defined as any element with an atomic number greater than 2, meaning any element except hydrogen and helium. The term semi-metal has different meanings in physics and chemistry. Bismuth is considered a semi-metal in physics, but chemists generally think of it as a metal. Terms like heavy metal are widely used, but they lack a precise definition and have been criticized as effectively meaningless. The scope of terms used can vary between different authors. For instance, IUPAC includes oganesson, a superheavy element in the noble gas group. However, some specialists in superheavy elements argue that oganesson shouldn't be considered a noble gas because it is predicted to be reactive due to relativistic effects, and it might not even be a gas at room temperature. In Japan, the group of alkaline earth metals sometimes doesn't include beryllium and magnesium because their behaviors differ from the heavier elements in Group 2. The most recently named elements, nihonium, moscovium, tennessine, and oganesson, complete the 7th row of the periodic table. Future elements will begin the 8th row. These elements may be referred to by their atomic numbers, for example, element 164, or by their systematic names, like unhexquadium for element 164, derived from the Latin and Greek words for 1, 6, and 4. Attempts to create these elements have been unsuccessful so far. Since 2018, researchers at the Riken Institute in Japan have been working to synthesize element 119, and institutions in the United States, Russia, and China plan their own efforts to create the first elements of the 8th period. If the 8th period followed the same pattern as the previous periods, it would have 50 elements, filling the 8s, 5g, 6f, 7d, and 8pa subshells in that order. However, by this stage, relativistic effects would cause significant differences from the Madelung rule. Many models have been proposed for the configurations of the elements in the 8th period, as well as how to represent these configurations in the periodic table. All of them agree that the 8th period should begin like the previous ones, with 2 elements, 119 and 120. After that, the large energy overlaps between the 5G, 6F, 7D, and 8P subshells make them begin to fill at the same time, which creates confusion about how to separate the specific 5G and 6F series. Elements 121 through 156 do not fit well into any previous group of elements in the earlier sections of the table. While they have sometimes been placed into the 5G, 6F, and other series to reflect their electron configurations, they don't behave like other elements from these series. Eric Sherry has raised the question of whether the periodic table should consider the breakdown of the Madelung rule in this region, or if these exceptions should be ignored. At this point, the electron distribution in elements like oganesson is expected to be fairly uniform, with no clear shell structure remaining. It takes 54 elements instead of 50 to reach the next noble element after element 118. While models generally agree about the chemistry of elements 157 through 172, there is some disagreement about whether the periodic table should reflect chemical similarities or whether it should reflect the likely formal electron configurations, which are expected to be quite different from the earlier periods. After element 172, things become much more complicated. The energy level of the 1s electron is expected to become imaginary, which does not pose an electronic limit to the periodic table, but it does create a challenge for calculations. It is still unclear how to incorporate such states into the calculations needed to define the periodic table beyond this point. The stability of atomic nuclei will likely be the key factor in limiting the number of possible elements. This depends on the balance between the repulsion between protons and the strong force that holds protons and neutrons together. Protons and neutrons, like electrons, are arranged in shells, and closed shells can greatly increase stability. Superheavy nuclei exist because of such shell closures, likely occurring around 114 to 126 protons and 184 neutrons. These superheavy nuclei are likely near a predicted island of stability, where some superheavy elements may have a longer lifespan than expected. Predictions for the longest-lived elements range from microseconds to millions of years, although these are based on extrapolations into unknown areas of the chart of Nuclides, and uncertainties need to be considered. As more closed shells are passed, the stabilizing effect fades, and superheavy elements with more than 184 neutrons are expected to have very short life, and superheavy elements with more than 184 neutrons are expected to have very short lifetimes, likely breaking apart in less than 1/4,000,000th of a second. If this is true, then it may not make sense to classify them as chemical elements, as the nucleus would not survive long enough to form an electron cloud. However, the predicted half-lives are highly model-dependent and vary greatly. The intense repulsion between protons may result in unusual nuclear shapes like bubbles, rings, and tori, further complicating predictions. It is unclear whether further shell closures exist, and even if they do, it's uncertain whether they would allow such heavy elements to exist. The periodic table may effectively end around element 120, as elements beyond that would be too short-lived to study or have meaningful chemistry. The discovery of new elements could be approaching its end. If there is a proton shell closure beyond 126, it is likely to occur around 164. This would mean that the area where the periodic table breaks down also aligns with the region of nuclear instability between shell closures. Alternatively, quark matter could become stable at very high atomic numbers. In this case, instead of protons and neutrons, the nucleus would be made up of freely moving quarks. This could create a continent of stability rather than an island. Even if elements from the 8th period can exist, producing them would be very challenging, especially as the atomic number increases. While elements 119 and 120 are expected to be possible with current technology, the creation of elements beyond them will require new methods, if they can even be produced at all. Experimentally studying these elements chemically would also be a significant challenge. The periodic table has been represented in many different ways. The standard table is just one version, and within 100 years of Mendeleev's table appearing in 1869, Edward G. Mazars collected around 700 different versions. Many tables maintain the rectangular layout, including Charles Janet's left-step periodic table and the modernized version of Mendeleev's original 8-column design, which is still used in Russia. Other tables have been designed with more creative shapes, such as spirals, circles, and triangles. Alternative periodic tables are often created to highlight specific chemical or physical properties that may not be as noticeable in traditional tables. These tables may emphasize certain aspects of chemistry or physics more than others. The standard format remains the most common, but discussions continue about whether one version of the table is better than the others. Janet's left-step table is gaining attention as a potential optimal version because it clarifies the role of helium as an S-block element and increases regularity in the table. It follows the Madelung rule more closely, with each period corresponding to a single value of n plus L. Sherry has argued that this version of the table makes more sense from a quantum mechanics perspective, focusing on atomic properties rather than chemical behavior. This left-step table matches the order in which electron shells are ideally filled, according to the Madelung rule. While the actual electron configurations of some elements differ from the predictions of the rule, they are always close, and in many cases, the Madelung rule remains a useful guide. In the world of chemistry, scientists noticed certain repeating patterns in the properties of elements. These patterns are known as periodic trends, and they help us understand how elements behave based on where they are placed in the periodic table. These trends became clear thanks to a brilliant Russian chemist named Dmitry Mendeleev, who made his groundbreaking discovery in the year 1863. Mendeleev built the first version of what we now call the periodic table. He carefully arranged the elements by their atomic weights and left empty spots where he believed undiscovered elements would eventually fit. Amazingly, his predictions came true. He accurately guessed the existence and properties of 3 unknown elements which were later discovered and named gallium, scandium, and germanium. Later on, in the early 20th century, an English physicist named Henry Moseley made an important improvement. He realized that if the elements were arranged by atomic number, which is the number of protons in an atom, instead of atomic weight, the table made even more sense. Elements with similar properties naturally lined up in groups. Now, let's explore the main periodic trends that scientists study. The atomic radius is the distance from the center of an atom, called the nucleus, to the outermost electron. Think of it as how wide an atom is. As we move from left to right across a row, called a period, on the periodic table, the atomic radius gets smaller. This is because atoms gain more protons, which pull the electrons closer to the nucleus. On the other hand, as we move down a column, called a group, the atomic radius gets larger. This happens because a new electron shell is added with each new element, making the atom bigger. The nuclear charge is simply the number of protons in the nucleus. As we go left to right across a period or top to bottom down a group, the nuclear charge increases because there are more protons. However, in atoms with many electrons, the outer electrons don't feel the full pull of the nucleus. This is due to something called the shielding effect, where inner electrons block some of the attraction from the nucleus. The amount of nuclear pull that the outer electrons actually feel is called the effective nuclear charge. From left to right, this effective nuclear charge still increases, making the atoms more tightly packed. But from top to bottom, as more electron shells are added, the shielding increases and the effective nuclear charge decreases. Ionization energy is the amount of energy needed to remove an electron from a neutral atom in its gas form. The first time you remove an electron, it's called the first ionization energy. Removing the second one takes even more energy and is called the second ionization energy, and so on. As you move left to right across a period, ionization energy increases. That's because the atoms are smaller and their electrons are held more tightly. But when you move down a group, ionization energy decreases because the electrons are farther from the nucleus and easier to remove. Electron affinity is the amount of energy released when an atom gains an electron and becomes negatively charged, an anion. As we go left to right across a period, electron affinity increases because atoms become more eager to attract electrons due to stronger nuclear charge and smaller size. When going down a group, electron affinity usually decreases because atoms are larger and the nucleus doesn't pull as strongly on extra electrons. Interestingly, even though fluorine is very small and very electronegative, it doesn't have the highest electron affinity. That title goes to chlorine. Fluorine is so small that adding another electron causes a lot of repulsion among its tightly packed electrons. Electronegativity is an atom's ability to pull shared electrons toward itself in a chemical bond. It's not measured in regular units, but instead we use a special scale called the Pauling scale, created by chemist Linus Pauling. On this scale, fluorine is the most electronegative element and cesium is one of the least. As you go left to right across a period, electronegativity increases because atoms are smaller and pull electrons more strongly. Going down a group, electronegativity decreases because atoms get larger and the nucleus's pull becomes weaker. There's an interesting twist in group 13, also known as the boron family. Electronegativity decreases from boron to aluminium, but then increases again as you go further down the group. This is due to poor shielding by d and f electrons, which allows the nucleus to pull harder on electrons. The valency of an atom tells us how many electrons it needs to gain or lose to become stable. Atoms with 1 to 8 valence electrons, the ones in the outermost shell, have different valencies depending on how close they are to having a full outer shell. From left to right across a period, the number of valence electrons increases, usually from 1 to 8. However, valency first increases from 1 to 4, then decreases back down to 0 when we reach the noble gases, which are already stable. Going down a group, the number of valence electrons usually stays the same, so elements in the same group often have the same valency. But this isn't always true for heavier elements, like transition metals and F-block elements, which can have variable valency due to their unique electron arrangements. As you move down a group, elements tend to become more metallic. Their outer electrons are less tightly held, so they can conduct heat and electricity more easily. From left to right across a period, elements become less metallic and more non-metallic. Nonmetals are better at holding onto their electrons and often form gases or brittle solids. Electrophiles are substances that want electrons. Their tendency to accept electrons is called electrophilicity. Nucleophiles are substances that have extra electrons and are ready to donate them. Their tendency to give electrons is called nucleophilicity. As you go left to right across the periodic table, electronegativity increases, so nucleophilicity usually decreases. Atoms hold on to their electrons more tightly. At the same time, electrophilicity increases because atoms are more eager to grab electrons. However, these properties also depend on the specific chemical environment. So, while periodic trends give us a good idea, the actual behavior of an element in a reaction can vary. Oganesson is a man-made chemical element, which means it doesn't exist naturally and has to be created in a laboratory. It has the symbol Og, and its atomic number is 118, which makes it the heaviest known element on the periodic table. This element was first made in the year 2002 by a group of Russian and American scientists working together at the Joint Institute for Nuclear Research, located in Dubna, a town near Moscow, Russia. More than a decade later, in December of the year 2015, it was officially recognized as one of 4 brand new elements by a special committee called the Joint Working Party. This committee is made up of 2 major international scientific organizations, IUPAC and IUPAP. The name Oganesson was formally approved on the 28th of November 2016. The element was named in honor of Yuri Oganessian, a well-known nuclear physicist who played a key role in discovering very heavy elements like this one. Oganesson is not only the heaviest element ever discovered, but it also has the largest atomic mass. On the periodic table, it belongs to a group called the P block and is part of group 18, the same group as the noble gases like helium and neon. It is also the very last element in period 7. So far, only one type of Oganesson atom has been made. This version is called Oganesson 294, and it is extremely unstable. It breaks apart almost instantly, within just 7/1000ths of a millisecond. By the year 2025, only 5 atoms of Oganesson had ever been created. Because of how rare and unstable it is, scientists have not been able to study how it behaves chemically in real-life experiments. However, based on theoretical calculations, experts believe it might actually be a solid at room temperature and could be much more reactive than the other noble gases, which are usually very unreactive. Creating a super-heavy element like Oganesson is no simple task. It involves smashing together 2 atomic nuclei, one heavier and one lighter. This kind of nuclear reaction works best when the 2 atoms have very different sizes. In fact, the more unequal the 2 are in mass, the more likely they are to combine. Here's how it works. Scientists take atoms of a heavier element and turn them into a target. Then, they fire a beam of lighter atoms at the target at extremely high speeds. These speeds are so fast that the beam particles can reach up to 1/10 the speed of light. The reason they have to go so fast is because atomic nuclei all have a positive charge and naturally repel each other, like the same ends of a magnet. To overcome this repulsion, the atoms must get extremely close, close enough for the strong nuclear force to take over and pull them together. But if the beam is too powerful, it can destroy the lighter nucleus before fusion happens. Even when the two nuclei get close enough, they usually don't stick together. Instead, they might just bounce off each other or break apart. This happens because the electrostatic repulsion is still trying to tear the newly forming nucleus apart. The chance of fusion actually happening depends on something called the cross-section, which is like a probability number that tells scientists how likely the atoms are to merge. Sometimes, quantum mechanics gives the nuclei a little help by allowing them to tunnel through the repulsion barrier. If they manage to stay together long enough, their energies balance out, and a new, heavier nucleus is formed. This new nucleus is highly excited, meaning it's full of extra energy and very unstable. When a new nucleus is created, it doesn't last long. It can break apart right away, or it might lose its extra energy by releasing a few neutrons. If it doesn't release neutrons, it might give off a type of light energy called a gamma ray. All of this happens in just a tiny fraction of a second, about 1/10,000 trillionth of a second. According to the rules set by the IUPAC and IUPAP, a new element is only officially considered discovered if its nucleus survives for at least 100 trillionths of a second. That's because this is the estimated time it takes for the nucleus to attract electrons and start acting like a chemical element. After the fusion reaction, the beam continues into a device called a separator. This tool helps to separate the newly created nucleus from all the other particles. If the new atom survives the trip through the separator about 1/1,000,000th of a second, it gets caught by a special detector. This detector marks where the atom landed, how much energy it had, and when it arrived. It also tracks when and how it decays. The stability of any atomic nucleus depends on the strong nuclear force, which holds the nucleus together. But this force only works over very short distances. In big atoms like oganesson, the outer protons and neutrons are too far from the center to feel this force strongly. At the same time, protons push against each other because they all have positive charges. Unlike the strong force, this repelling force works over long distances and gets stronger as more protons are added. So, as atoms get heavier, this repulsion becomes a bigger problem. It makes the nucleus more likely to fall apart. Superheavy elements like oganesson often decay in two main ways: alpha decay and spontaneous fission. In alpha decay, the nucleus emits an alpha particle, 2 protons and 2 neutrons. In spontaneous fission, the whole nucleus splits into 2 or more smaller parts. Most atoms that emit alpha particles have more than 210 protons and neutrons combined. The lightest atom known to split apart on its own through spontaneous fission has 238 nucleons. These decay processes are slowed down by energy barriers, but thanks to quantum tunneling, the atoms can still break apart. Alpha particles are small and stable enough that when they're emitted, they leave some energy behind, which helps push them out of the nucleus. Spontaneous fission, on the other hand, creates different results each time it happens. As atoms get even heavier, spontaneous fission becomes much more likely. For example, spontaneous fission happens 10 million trillion times faster in nobelium, element 102, than it does in uranium, element 92. In fact, early theories once suggested that very heavy elements wouldn't last more than a tiny instant because the force pulling them apart would be too strong. Later models, though, suggested the idea of an island of stability, a group of super heavy elements with special arrangements of protons and neutrons that would make them more stable. These atoms would mainly decay through alpha emission and survive longer. Newer experiments hint that this island might be farther away than first thought, but also show that some super heavy atoms are more stable than expected, thanks to special shell effects in their nuclear structure. When a nucleus decays by emitting an alpha particle, it's easy to track. The energy of the particle and its position tell scientists exactly what kind of decay occurred. If the decay chain leads to a known atom, they can figure out what the original atom was. But in spontaneous fission, things get tricky. Since the nucleus splits into random fragments, it's much harder to tell where it came from. That's why alpha decay is usually the best way to confirm that a super-heavy element like oganesson has been made. When scientists try to create a brand new, super-heavy element, they have to rely on the tiny bits of information collected by sensitive machines called detectors. These detectors tell them three things about any particle that hits them: where it hit, how much energy it had, and when it arrived. They also capture similar details when that particle breaks down or decays into smaller parts. By carefully studying all this data, physicists try to figure out whether what they observed really came from a brand new element, or if it could have come from something else. But often, the evidence isn't strong enough to say for sure. Mistakes have been made before, and sometimes scientists have misread the results. The idea of a seventh noble gas, a gas that doesn't easily react with other elements, was imagined not long after the first ones were discovered. After helium, neon, argon, krypton, xenon, and radon were identified, a Danish chemist named Hans Peter Jørgen Julius Thomsen made an exciting prediction in April of the year 1895. Just 1 year after argon had been found, he said there might be a whole group of similar unreactive gases. He believed the seventh gas in this group would belong to the same long row of elements that includes thorium and uranium. He even guessed its atomic weight would be around 292, which is very close to the 294 now known for oganesson, the only confirmed isotope of this element. Then, in the year 1922, the famous Danish physicist Niels Bohr added to the prediction. He said this new noble gas would have the atomic number 118, and he even predicted how its electrons would be arranged: 2, 8, 18, 32, 32, 18, and 8. This matches what modern scientists believe today. Later, in the year 1965, a German chemist named Aristide von Grosser wrote an article imagining what the properties of this mysterious element might be like. But it took a long time for science to catch up. It wasn't until 107 years after Thomson's early guess that oganesson was finally created in a lab. Still, scientists haven't been able to study its chemistry closely enough to say whether it really behaves like a heavy version of radon. In the year 1975, an American chemist named Kenneth Pitzer suggested that oganesson might be a gas or a very volatile liquid because of strange effects seen in very heavy elements known as relativistic effects. In the late part of 1998, a Polish physicist named Robert Smolanchuk ran some complex calculations. He studied how atomic nuclei might fuse together to create super-heavy elements, including oganesson. He suggested it might be possible to make element 118 by fusing atoms of lead with krypton under very specific conditions. Surprisingly, he predicted that this fusion would be just as likely as an earlier fusion of lead and chromium that had made element 106, called seaborgium. This went against what most scientists thought, that the chances of creating super-heavy elements would shrink dramatically as the atomic number went up. In the year 1999, scientists at the Lawrence Berkeley National Laboratory in California decided to test this idea. They reported that they had created both element 118 and element 116. They published their results in a respected journal called Physical Review Letters, and shortly after, in Science. They claimed that they had caused lead atoms, atomic number 82, to collide with krypton atoms, atomic number 36, and this produced a new element with atomic number 118. But in the year 2001, they took it all back. Other labs had tried to repeat the experiment but failed, and even the original team couldn't get the same results again. In June of 2002, the lab director announced that the original data had been faked by one of the lead scientists, Viktor Ninov. Later experiments and theories confirmed that it really was harder to make super-heavy elements by fusing lead or bismuth with lighter elements, just as earlier predictions had said. The first real proof that oganesson had been created came later, in the year 2002, at the Joint Institute for Nuclear Research, JINR, in Dubna, Russia. A team of Russian and American scientists, led by nuclear physicist Yuri Oganessian, managed to detect what seemed to be Oganesson atoms, but they didn't rush to announce it. The decay energy of Oganesson matched that of a common contaminant, polonium-212 meters, so they waited until another experiment in 2005 gave clearer results. That second test used a slightly more powerful beam, 251 mega-electron volts instead of 245, and a thicker target. On October 9, 2006, the team announced that they had indirectly detected 3 or possibly 4 atoms of Oganesson-294. 1 or 2 had been seen back in 2002, and 2 more were seen in 2005. In the year 2011, an international science panel called IUPAC reviewed the findings. They said that while the evidence for Oganesson-294 was consistent, there wasn't yet a firm connection to any previously known nucleus, so it didn't fully meet the standards for a discovery. Making even a few atoms of Oganesson is incredibly hard. The chance of success, called the fusion cross-section, is extremely tiny, about 0.3 to 0.6 picobarns, which is about 3 to 6 times 10 to the power of minus 41 square meters. The experiment had to run for 4 straight months, using a huge beam of 2.5 times 10 to the power of 19 calcium ions just to see the first atom. Still, the scientists were very confident that their results were real. The odds of the detections being random were less than 1 in 100,000. In these experiments, 3 Oganesson atoms decayed by releasing alpha particles, which are helium nuclei. A possible 4th atom broke apart through spontaneous fission. The half-life, the time it takes for half the atoms to decay, was found to be around 0.89 milliseconds, though with a lot of uncertainty because only a few atoms were seen. They found that the livermorium-290 decayed in exactly the same way as the product of the Oganesson decay chain. This confirmed that the original atoms had indeed been Oganesson. But livermorium-290 is also unstable. It lives for only about 14 milliseconds before turning into flerovium-280. That, too, is unstable, and it may decay either by alpha emission or by splitting apart through fission into copernicium-282, which also undergoes fission. In December of the year 2015, the Joint Working Party of IUPAC and IUPAP officially recognized the discovery of Oganesson. They gave credit to the Russian-American team at Dubna and Lawrence Livermore. Their decision was based on confirmations in 2009 and 2010 of the properties of one of Oganesson's decay products, flerovium-286, at the Lawrence Berkeley lab. Another decay chain matching Oganesson-294 was also seen in a 2012 experiment. Interestingly, that experiment had originally aimed to make tennessine-294 using berkelium-249, but since berkelium decays quickly, much of it had already turned into californium-249, accidentally leading to the creation of Oganesson instead. From the beginning of October in the year 2015 to early April in the year 2016, a group of scientists working in Dubna, Russia, carried out a fascinating experiment. They used a beam of calcium-48 atoms and aimed it at a special target made from a mix of different isotopes of the element californium, specifically californium-249, californium-250, and californium-251. Their goal was to create even heavier forms, or isotopes, of the super-heavy element Oganesson, including Oganesson-295 and Oganesson-296. To do this, they tried 2 different beam energies, 252 million electron volts and 258 million electron volts. At the lower energy level, they managed to observe just 1 atom. Its pattern of decay matched what was already known from Oganesson-294, which eventually breaks apart into a lighter element called flerovium-286. However, at the higher energy level, no atoms were seen at all. The experiment had to be stopped because glue from the machine's internal structure accidentally covered the target. This blocked the tiny newly formed atoms from reaching the detectors. Despite these setbacks, the reaction used in this experiment might still be useful in creating other versions of oganesson, such as oganesson 293, oganesson 297, and their decay products like livermorium 289. Scientists also believe that using different materials, like curium 248 combined with titanium 50, might also lead to the creation of oganesson 295 or oganesson 296. In the summer of 2016, a Japanese research center called Riken began searching for oganesson 295 using this new method. Unfortunately, they did not find any atoms at that time, though they plan to try again in the future. They did not publish a detailed analysis or report how likely it was for the element to form. These heavier forms of oganesson might turn out to be more stable than the ones made so far, and this would help scientists study the chemistry of this mysterious element more closely. Before oganesson officially had a name, it was sometimes referred to by its placeholder name based on a system created by the famous Russian chemist Dmitry Mendeleev. Back then, it was called eka-radon, which means the element after radon. In the past, radon was known as emanation, so some older sources even called oganesson eka-emanation. In the year 1979, a group called IUPAC, the International Union of Pure and Applied Chemistry, gave it the temporary name ununoctium, with the symbol UO. This name just meant 118, referring to its position as the 118th element on the periodic table. Although this name was supposed to be used until the element was officially discovered, many scientists ignored it and simply called it element 118, or even just 118. Before this, in the year 2001, scientists in Berkeley, California, had claimed to discover the element and wanted to name it Gyorsium, after one of their leading researchers, Albert Ghiorso. However, that claim was later withdrawn when they could not reproduce the results. The true discovery came in the year 2006 from the Russian team. According to IUPAC rules, the scientists who discover a new element get to suggest a name for it. In 2007, the head of the Russian laboratory said they were thinking of two possible names: Flyorium, to honor Georgy Flyorov, who founded the lab in Dubna, and Moscovium, in honor of the Moscow region where the lab is located. Although American scientists had helped by providing the Californium target, the Russians believed the element should carry a name reflecting their country's achievement, since their laboratory was the only one in the world capable of making such super-heavy elements. Eventually, those names were given to different elements. Element 114 became flerovium, and element 115 became moscovium. Another element, number 116, was named livermorium, after the American laboratory in Livermore. Traditionally, noble gases, like helium, neon, and radon, have names that end in -on. However, when IUPAC set naming rules for new elements, they originally required all new element names to end in -ium, even for noble gases and halogens, which usually end in -ine. The placeholder name ununoctium followed that rule. But in 2016, IUPAC updated the guideline to allow noble gases in Group 18 of the periodic table to go back to using the traditional -on ending. On the 23rd of March in the year 2016, the scientists who had worked on discovering elements 115, 117, and 118 held a conference call to decide on names. For element 118, they asked Yuri Oganessian, one of the pioneers of super-heavy element research, to leave the call. Then, the rest of the team voted unanimously to name the element oganesson in his honor. Oganessian had dedicated more than 60 years to the field, helping to develop the techniques that made the discovery of elements from 107 through 118 possible. Later, there was a brief discussion about whether the name should be spelled Oganesson to match the Russian pronunciation more closely. But Oganessian and his team declined, explaining that the spelling Oganesson followed an older tradition of converting names into Latin using French rules and would be more recognizable internationally. In June of 2016, IUPAC announced that the new element would officially be named Oganesson, with the symbol Og. This name became official on the 28th of November that same year. The formal naming ceremony for Oganesson, along with two other new elements, Moscovium and Tennessine, was held on the 2nd of March in the year 2017 at the Russian Academy of Sciences in Moscow. In a 2019 interview, when asked what it felt like to see his name beside those of great scientists like Einstein, Mendeleev, the Curies, and Rutherford on the periodic table, Yuri Oganessian humbly smiled. It was a fitting reward for a lifetime of groundbreaking work in nuclear science. Despite all the excitement around its discovery, Oganesson remains mysterious. Scientists have not yet been able to measure its physical or chemical properties directly. This is because it is extremely difficult and expensive to make, and it falls apart almost instantly. So, for now, scientists can only rely on predictions. As elements get heavier and have more protons in their nuclei, they become less stable. For example, curium, element number 96, has the longest-lasting isotope among these super-heavy elements. Its most stable form, curium-247, lives thousands of times longer than the ones that come after it. Elements with more than 101 protons all decay quickly. None of them last longer than 30 hours. In fact, no element beyond lead, which is number 82, has any stable forms. This growing instability is caused by the strong repulsion between the many positively charged protons in the nucleus, which becomes too much for the strong nuclear force to hold together. Based on early calculations, scientists thought elements with more than 104 protons shouldn't be able to exist at all. However, in the 1960s, researchers proposed a fascinating idea. If an element had exactly the right number of protons and neutrons, specifically 114 protons and 184 neutrons, it might become much more stable. This area of the periodic table was nicknamed the Island of Stability. While scientists haven't reached this island yet, the fact that super-heavy elements like Oganesson exist at all proves that this special stabilizing effect is real. As scientists get closer to this island, the lifetimes of these heavy atoms seem to increase step by step. Oganesson is very radioactive. It decays by releasing alpha particles and through a process called spontaneous fission. Its half-life, how long it takes for half of the atoms to break apart, is less than 1,000th of a second. Still, that's actually longer than some scientists had expected, which makes Oganesson all the more intriguing. Scientists using special physics models that deal with quantum tunneling, a process that lets particles pass through barriers, have predicted that there could be heavier versions, called isotopes, of Oganesson that last a bit longer than the one we've already created. These new versions might live for about 1 millisecond, which is 1,000th of a second. That might not seem like much, but for such a heavy and unstable element, it's actually quite promising. Some computer models have suggested that other isotopes of Oganesson, such as those with mass numbers 293, 295, 296, 297, 298, 300, and 302, could be more stable than the known isotope called 294 Oganesson. Among these, scientists believe that the isotope with mass number 297 could be the most likely candidate to survive the longest, making it a top target for future experiments. Even heavier isotopes, like those around mass number 313, might last even longer. Some of the lighter ones, like from 291 to 295, could possibly be created as byproducts, or daughters, when other super-heavy elements, such as element 120, are made using combinations of californium or curium, and lighter elements like titanium or calcium. When the half-life of the already created oganesson isotope, 294, was calculated using a quantum tunneling model, it was predicted to be around 0.66 milliseconds. Later models using slightly different theories gave similar results. Oganesson is part of a group of elements called noble gases, group 18 in the periodic table. These elements are famous for not reacting much with anything. That's because they have full outer shells of electrons, which makes them very stable. Oganesson is expected to have the same kind of full outer shell, with electrons arranged in a pattern called 7s2, 7p6. Because of this, many scientists once thought oganesson would behave like radon, the noble gas just above it in the periodic table. But recent calculations show something surprising. Oganesson might actually be much more reactive than radon. In fact, it could be even more chemically active than some other super-heavy elements like flerovium and copernicium, which are related to lead and mercury. This unexpected reactivity is thought to be caused by a unique stretching and weakening of oganesson's outer electrons, along with powerful internal forces called spin-orbit interactions, which mix up the electrons in strange ways. Even more interesting, oganesson might actually attract extra electrons and hold onto them, releasing energy in the process. This means it has what's called a positive electron affinity, which is very unusual for noble gases. They usually don't like grabbing extra electrons at all. The only reason oganesson behaves this way is because of some mind-bending effects that happen when very heavy atoms are involved, especially those predicted by quantum electrodynamics, QED. In fact, QED calculations suggest that oganesson's electron affinity should be about 0.080 electron volts, with a small uncertainty. Computer simulations using a method called Monte Carlo predicted that oganesson melts at about 325 Kelvin, which is around 52 degrees Celsius, and boils at about 450 Kelvin, around 177 degrees Celsius. This means that, unlike other noble gases that are usually gases at room temperature, oganesson would probably be a solid. Oganesson is also expected to be highly polarizable. In simple terms, this means its cloud of electrons can be pushed and pulled around more easily than in most elements, making it behave strangely in electric fields. Because of this, it should have a low ionization energy. That's the amount of energy needed to remove one of its electrons. Its first ionization energy might be around 860 kilojoules per mole, which is even lower than metals like platinum and gold. Its second ionization energy is expected to be around 1,560 kilojoules per mole. Another wild feature of oganesson is how the structure of its electrons, and even the particles in its nucleus, is completely changed by relativistic effects, which come from Einstein's theory of relativity. For example, its electrons don't sit in neat, organized shells like in lighter elements. Instead, they are spread out like a mist, something physicists call a Fermi gas. Even the protons inside the nucleus might be distributed oddly, with fewer at the center, forming a semi-bubble. Oganesson may also behave like a semiconductor, a material that can conduct electricity under certain conditions. This is very different from other noble gases like radon, which are all insulators that don't conduct electricity at all. Right now, the only confirmed oganesson isotope, number 294, decays too quickly for scientists to study its chemical behavior directly. So, no one has actually made any oganesson compounds in the lab yet. Still, scientists have been running calculations on possible oganesson molecules since the year 1964. If oganesson had a very high ionization energy like other noble gases, it would be hard to make it react with anything. But researchers now believe that it's more reactive, and it might form compounds more easily than expected. For example, oganesson might form a weak bond with another oganesson atom in a molecule called Og2, with a bond that is 4 times stronger than a similar bond in radon gas. In the molecule OGH+, oganesson bonded with hydrogen, the bond is predicted to be even weaker, mostly held together by van der Waals forces, which are the weakest type of chemical interactions. However, oganesson seems to form more stable compounds with very electronegative elements like fluorine. For example, compounds like OGF2, oganesson difluoride, and OGF4, oganesson tetrafluoride, might exist, with oxidation states of +2 and +4. These compounds would be stabilized by the same spin-orbit effects that make oganesson more reactive. A theoretical reaction between oganesson and fluorine gas could release about 106 kilocalories per mole of energy, nearly half of that just from spin-orbit interaction alone. In contrast to xenon tetrafluoride, XEF4, which has a flat square shape, OGF4 would most likely have a tetrahedral, three-dimensional shape due to its unique electron structure. A compound like OGF6 with oganesson in a +6 state would probably be too unstable to exist. Oganesson's bonds with fluorine are predicted to be more ionic than covalent, meaning the electrons aren't shared equally. This makes oganesson fluorides non-volatile, meaning they don't easily turn into gas. The same ionic nature might allow oganesson to bond with chlorine as well, forming Og-Kel bonds. Interestingly, a compound called OgTS4, which combines oganesson with tennessine, another super-heavy element, is predicted to be chemically stable, at least in theory. Ununennium, also called AK francium or element 119, is a chemical element that scientists believe exists, but it hasn't been discovered yet. For now, it is known by the temporary name ununennium and has the symbol Ue. This name and symbol were given by the International Union of Pure and Applied Chemistry, IUPAC, to use until the element is officially discovered and given a permanent name. In the periodic table, ununennium is expected to be an alkali metal like sodium or potassium. It should also belong to the S block, which includes elements with similar properties, and it would be the very first element in the 8th period of the table. Out of all the elements that have not yet been made in a lab, ununennium is the lightest. Scientists have been trying to create ununennium since the year 2018 at the Riken Research Institute in Japan. Other research centers also want to try making it. For example, the Joint Institute for Nuclear Research in Dubna, Russia, has future plans to attempt its creation, although they haven't said exactly when. A facility in China, known as the Heavy Ion Research Facility in Lanzhou, or HIRFL, also plans to join the race. However, researchers believe that making ununennium will be much harder than creating any of the elements just before it on the periodic table. Because ununennium would be the 7th alkali metal, scientists expect it to act like the others in this group. However, strange and powerful effects that happen in very heavy atoms, called relativistic effects, might make ununennium behave in unexpected ways. For instance, it might not be as reactive as francium or cesium, and instead act more like potassium or rubidium. Normally, alkali metals have just one main type of chemical behavior. They form a +1 charge when reacting. But ununennium might surprise scientists by also showing unusual +3 or even +5 oxidation states, which would make it very different from the rest of its family. To create a new super-heavy element like ununennium, scientists perform an extraordinary kind of experiment. They smash together two different atomic nuclei, one heavy and one lighter. The heavier material is shaped into a target, and the lighter one is turned into a fast-moving beam that strikes the target. But there's a problem. Atomic nuclei are all positively charged, and like charges repel each other. So the two nuclei naturally push away from each other. To overcome this, scientists give the beam nuclei an enormous amount of energy so they can get close enough for the strong nuclear force, the force that holds atomic nuclei together, to take over. The beam particles can reach speeds as fast as 1/10 the speed of light. But there's a fine balance. If the beam is too energetic, the particles might just break apart instead of fusing. Even if the two nuclei do manage to get close, that still doesn't guarantee success. Usually, they only stay together for a tiny fraction of a second, about 100 billion billionths of a second. That's 10 to the negative 20th seconds, before falling apart again. The goal is for them to stick together long enough to form a brand new atomic nucleus. The chance that this kind of fusion will happen is measured by something called a cross-section, which tells scientists how likely it is that the beam will hit the target just right. Sometimes, instead of jumping over the energy barrier caused by electrostatic repulsion, the nuclei tunnel through it thanks to a strange quantum effect. If fusion does occur, the newly created nucleus is extremely unstable. It's full of extra energy. This unstable, short-lived state is called a compound nucleus. It might break apart instantly, but if it survives just a bit longer, it may release some of its energy by throwing out a few neutrons or releasing a burst of energy called a gamma ray. This all happens in less than 1/4,000,000th of a second, about 10 to the negative 16th seconds. If the nucleus holds together for at least 1/10,000th of a trillionth of a second, 10 to the negative 14th seconds, then scientists consider it to be a real chemical element, since that's about how long it takes to pick up electrons and show its chemical behavior. After the beam hits the target, any new nuclei formed are carried along into another part of the experiment called a separator. This special chamber filters out everything except the brand new nuclei, which are then sent to a detector. The detector stops the nucleus and records exactly where it landed, how much energy it had, and the exact time it arrived. All this must happen in just 1/1,000,000th of a second. If the new nucleus falls apart before that, it won't be detected. When the new nucleus decays, which happens very quickly, the detector records that too, when it happened, how much energy was released, and exactly where it occurred. By comparing this information, scientists can figure out whether they've created a brand new element or not. The strong nuclear force holds protons and neutrons together inside the nucleus. But this force only works over a very short distance. As the nucleus gets bigger and heavier, this force becomes less effective, especially at the edges. Meanwhile, the repulsion between the positively charged protons doesn't weaken, it keeps getting stronger. The strong nuclear force increases in strength as more particles are added to the nucleus, but the repelling electric force increases even faster. This creates a situation where the nucleus is under enormous internal pressure and it becomes very unstable. That's why almost all the known super-heavy elements fall apart quickly. Most of them decay by releasing alpha particles, which are made of 2 protons and 2 neutrons, or by splitting into 2 smaller nuclei, a process called spontaneous fission. These decay methods are a result of the intense internal struggle between the forces holding the nucleus together and the forces trying to tear it apart. To give you an idea, most elements that emit alpha particles have more than 210 nucleons, protons and neutrons combined, and the lightest element known to undergo spontaneous fission has 238 nucleons. Even though barriers exist that can delay decay, quantum tunneling can still allow these decays to happen. That's why even the most massive atoms ever created usually vanish in fractions of a second. Alpha particles, which are small clusters made of 2 protons and 2 neutrons, are often released when certain unstable atoms break down in a process called radioactive decay. One big reason for this is that the mass of an alpha particle, when you divide it by the number of its parts, called nucleons, is low. That means there's still some leftover energy that can be used to push the alpha particle out of the atom's nucleus like a little rocket, giving it motion or kinetic energy. Another kind of nuclear event is called spontaneous fission. This happens when the repulsive electrical force between the positively charged protons inside the nucleus becomes too strong and literally tears the nucleus apart. Unlike alpha decay, where a single type of particle is emitted, spontaneous fission breaks the nucleus into many different pieces, and it doesn't always produce the same ones. As the number of protons in an atom, its atomic number, gets higher, spontaneous fission becomes more and more important. For example, the time it takes for half of a sample of atoms to undergo spontaneous fission, called the half-life, gets much shorter as you go from uranium, which is element number 92, to nobelium, element number 102. In fact, the half-lives decrease by a staggering 23 orders of magnitude across that range. The difference is even greater, 30 orders of magnitude, when going from thorium, element number 90, to fermium, element number 100. In the early days of nuclear science, scientists had a theory called the liquid drop model. This model predicted that very large atomic nuclei with around 280 particles inside would have no protection against splitting apart and would break almost instantly through spontaneous fission. But a newer model, known as the nuclear shell model, added something interesting. It suggested that when you reach nuclei with around 300 particles, they might actually become more stable again, forming what scientists call an island of stability. These special superheavy atoms would mostly undergo slower alpha decays instead of breaking apart quickly. Later discoveries hinted that this mysterious island of stability might lie farther away than scientists first thought. They also found that many nuclei between the long-lived heavy elements, called actinides, and the island of stability are stretched or deformed in shape. This stretching, combined with the effects of special arrangements of protons and neutrons, called shell effects, gives these atoms extra stability. Experiments on some lighter superheavy elements and others closer to the predicted island showed that these shell effects really do help make the atoms more stable than expected, even against spontaneous fission. When scientists detect alpha decay, they can usually figure out what the original atom was before it decayed. That's because alpha particles have a specific amount of energy, and the new atom created by the decay is known. If several alpha decays happen in a row, what's called a decay chain, and end with a well-known element, scientists can trace the steps backward to identify the original atom. All of this happens in the same physical spot, which confirms that the decays are related. Spontaneous fission, on the other hand, is much harder to track because it creates a mix of different elements each time, so you can't easily figure out what the original atom was just by looking at the pieces. When scientists are trying to create a new super-heavy element, the only clues they have come from special detectors. These detectors record where a particle lands, how much energy it has, and exactly when it arrives. Scientists look at this data and try to figure out if it could only have come from a brand new element or if it might be something else. But the data is often incomplete, and mistakes have been made in the past when interpreting these signals. Elements with atomic numbers from 114, flerovium, to 118, oganesson, were discovered using hot fusion reactions at the Joint Institute for Nuclear Research in Dubna, Russia. This method involved smashing atoms of actinide elements like plutonium through californium with a special kind of calcium called calcium-48. This version of calcium has extra neutrons and is unusually stable, which makes it great for these experiments. The term hot fusion comes from the fact that the new atom created in the collision has a lot of energy and is very excited. However, going beyond element 118 is much harder. Creating element 119, for example, would require using Einsteinium as the target, but that element is incredibly rare. Scientists would need tens of milligrams of it, yet so far, only micrograms have ever been made. An early attempt to make element 119 using Einsteinium and calcium-48 took place in the year 1985 at the Super Hilux Accelerator in Berkeley, California, but it didn't produce any atoms. To go further, scientists would need to use heavier projectiles than calcium-48, but this makes the nuclear reactions more balanced or symmetric, which actually lowers the chance of success. Making element 119 is pushing current technology to its limits. The reactions become harder, and any atoms that do form are expected to break down extremely fast, within just a few millionths of a second. Between the months of April and September in the year 2012, scientists at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany, tried to make atoms of element 119, also called ununenium, and element 120. They did this by firing titanium-50 atoms at a target made of berkelium-249. This reaction was thought to be the best option because it was the most asymmetric, increasing the chances of forming new elements. Berkelium-249 also decays into californium-249 fairly quickly. Its half-life is 327 days, so this allowed the researchers to look for two elements at once. Because the newly created atoms were expected to exist for just a few microseconds, the team used extremely fast electronics that could detect and record such quick events. Despite all their efforts, they did not detect any atoms of element 119 or 120. The experiment was supposed to continue until November of that year, but it was stopped early so the team could use the berkelium-249 to confirm the discovery of another element, tennessine, using calcium-48 instead. Later on, in January of the year 2018, a team at Riken in Waco, Japan, began searching for element 119 by using a different strategy. They bombarded targets made of curium-248 with a beam of vanadium-51 atoms. They picked curium because it was easier to get and prepare than the heavier elements like berkelium or californium. The curium-248 targets came from Oak Ridge National Laboratory in the United States, and Riken developed a powerful vanadium beam for the experiment. They started the work at a cyclotron, a type of particle accelerator, while they were upgrading their larger linear accelerators. That upgrade finished in the year 2020, and the experiments may continue until at least one atom is found. Interestingly, the search is being supported financially by the Emperor of Japan himself. If ununenium is created, it's expected to undergo 2 alpha decays, which would turn it into known forms of the element moscovium, specifically isotopes 287 and 288. These known forms then go through 5 or 6 more alpha decays. If this sequence is seen, it will confirm that ununenium was truly created. By September of the year 2023, scientists at Riken, a major research institute in Japan, had already spent 462 days running a special nuclear experiment. They were trying to create a brand new element using a reaction that involved smashing together 2 types of atoms, curium-248 and vanadium-51. This specific reaction was chosen not because it was the best one predicted by theory, but simply because the materials needed were easier to get. Interestingly, many experts believed that using a different reaction, one with berkelium-249 and titanium-50, might have worked better. That's because titanium-50 is quite similar to calcium-48, a very stable atom known as doubly magic, due to the special number of protons and neutrons it contains. Titanium-50 also has an even number of protons, 22, and experiments have shown that reactions involving projectiles with even numbers of protons usually have a better chance of success. Still, the Riken team stuck with their original plan. However, an advisory committee from the Riken Nishina Center gave them a warning. If the chances of success, called the cross-section, drop to just 5 femtobars without any results, the scientists should stop, rethink their approach, and only continue after making changes. As of August in the year 2024, the team was still running the experiment around the clock, 24 hours a day, 7 days a week. Meanwhile, over in Russia, the scientists at the Joint Institute for Nuclear Research, JINR, were also planning to try to create element 119 in the future, although they hadn't shared exactly when. In late 2023, JINR achieved something quite impressive. They managed to create a new version of element 116, called livermorium-288, by smashing uranium-238 with chromium-54. This success was surprising and exciting because they had never before created a super-heavy element using a projectile heavier than calcium-48. Originally, the goal of the experiment wasn't even to make livermorium. It was to study how likely it was for a reaction with chromium-54 to work, which would help prepare for the future creation of element 120. Encouraged by this result, JINR announced that they also plan to use chromium-54 to try making element 119 by bombarding americium-243. In China, researchers at the Heavy Ion Research Facility in Lanzhou, HIRFL, which is run by the Institute of Modern Physics under the Chinese Academy of Sciences, are planning to do the same kind of experiment, firing chromium-54 at americium-243 to try and create element 119. Right now, before it's discovered, scientists use a temporary name for element 119. According to Dmitry Mendelev's old system, it's called eka-francium because it's expected to be similar to francium. Under the 1979 rules of the International Union of Pure and Applied Chemistry, IUPAC, the element is temporarily called ununenium, with the symbol UA. This name will stay in place until the element is officially discovered, confirmed, and given a permanent name. Although textbooks and classrooms often use the name ununenium, scientists working in labs usually just call it element 119, or E119, or even just plain 119. Creating and studying elements this heavy is extremely difficult because their nuclei become more unstable as the atomic number increases. For example, curium, which is element 96, is already a lot less stable than lighter elements. As the atomic number gets even higher, the atoms become so unstable that they decay very quickly. In fact, all elements with atomic numbers higher than 101 break down in less than 30 hours, and none of the elements beyond lead, element 82, have any stable versions at all. Still, there's an unusual exception in this pattern. Around atomic numbers 110 to 114, some elements seem to last a little longer than expected. This surprising effect is called the island of stability. It was first suggested by the famous nuclear chemist Glenn Seaborg, who believed that certain combinations of protons and neutrons might create unusually stable super-heavy elements. For ununenium, element 119, predictions say that its isotopes, versions of the element with different numbers of neutrons, will decay very quickly. Most of them are expected to break down in just a few millionths of a second or microseconds. The most stable one might be ununenium-294, which could last about 485 microseconds. But when you include all the ways it could decay, some versions might survive only for a few tens of microseconds, barely enough time to detect them. Some scientists, like Fricker and Weber, suggested back in 1971 that a heavier isotope called ununenium-315 might last longer. However, making these heavier isotopes is not easy. If an isotope decays in less than 1 microsecond, it might disappear before it can even reach the detector. On top of that, we currently don't have any practical combinations of target and projectile atoms that can produce those heavier isotopes. Still, new theoretical models suggest something interesting. Scientists now believe that the so-called magic shell of stability that was expected at element 114 may not be as strong as they thought. Instead, elements 119 and 120 might be more stable than predicted. The next really stable, doubly magic nucleus might show up at element 122, especially with an isotope called ununbium-306. But making this one will be extremely difficult because it would decay too fast and would be very hard to produce. Among the more likely versions of ununenium to be created soon are ununenium-293 to ununenium-296. These might be made through what's called the 3-neutron and 4-neutron processes, using reactions like americium-243 plus chromium-48, or berkelium-249 plus titanium-50. Since ununenium would be the first element in the 8th row of the periodic table, it's expected to be an alkali metal, just like lithium, sodium, potassium, rubidium, cesium, and francium. All of these elements have one electron in their outermost layer, which they easily lose during chemical reactions. That makes them very reactive. Ununenium is predicted to follow this pattern, with one electron in the 80s orbital, but it might behave a bit differently from its lighter relatives. One big reason for these differences is something called spin-orbit interaction. This is a special effect that happens when electrons move so fast that their spin, a kind of built-in rotation, starts interacting with their motion around the nucleus. This effect becomes very strong in super-heavy elements because their electrons move at speeds close to the speed of light. In ununenium, this interaction changes the energy levels of its electrons. It lowers the energy of the 7p and 8s electrons, making them more stable. But even within the 7p group, 2 of the 6 electrons become much more stable than the other 4. Scientists call this subshell splitting. This strange effect might make it harder to remove the 8s electron and could allow the 7p electrons to take part in chemical reactions, which is unusual for alkali metals. Because of all these unique effects, ununenium might not follow the same chemical trends as its lighter cousins. In fact, the pattern of properties seen in alkali metals might actually reverse after cesium, all because of how the spin-orbit interaction changes the atom's behavior. Ununenium, also known as element 119, is expected to behave quite differently from the alkali metals above it on the periodic table. One of the most interesting things about this element is the way its outermost electron behaves. Because this electron is held in place more tightly due to powerful relativistic effects, it takes more energy to remove it. Scientists estimate that its first ionization energy, which is the energy needed to remove one electron from a neutral atom, is about 4.53 electron volts. That's higher than the ionization energies of all the alkali metals from potassium onwards. This effect is so strong that even unbiunium, element 121, is predicted to have a lower ionization energy, around 4.45 electron volts. That's unusual because in every other row of the periodic table, the alkali metal always has the lowest ionization energy. But in the 8th period, ununenium might not hold that title. Ununenium is also expected to attract electrons more strongly than cesium or francium. In fact, its electron affinity, which shows how much an atom wants to gain an extra electron, is predicted to be about 0.662 electron volts. That's quite high for an alkali metal and is similar to the values for cobalt and chromium, which are 0.662 and 0.676 electron volts, respectively. Another major consequence of these relativistic effects is a big drop in polarizability, which is a measure of how easily an atom's electron cloud can be distorted. For ununenium, it's expected to be just 169.7 atomic units, making it quite similar to sodium in this regard. Now let's imagine a hydrogen-like ununenium atom, one that has lost all its electrons except one, like a bare nucleus with a single electron left. In this case, that electron would be moving incredibly fast, so much so that its mass would be nearly 2 times that of a normal, motionless electron. To be exact, it would be 1.99 times heavier. For comparison, this factor is only 1.29 for hydrogen-like francium and 1.091 for hydrogen-like cesium. These high speeds are also caused by relativistic effects. These fast-moving electrons also pull closer to the nucleus, which shrinks the size of the atom. So, even though ununenium is a huge atom, its atomic radius is expected to be around 240 picometers, similar to that of rubidium, which has a radius of 247 picometers. Its metallic radius would also be smaller, around 260 picometers, and the ionic radius of UE+ is expected to be about 180 picometers. Ununenium might also be a bit unusual in how it changes state. It's predicted to have a melting point somewhere between 0 degrees Celsius and 30 degrees Celsius, meaning it could possibly be a liquid at room temperature. That's very rare for metals. Francium is thought to melt at around 8 degrees Celsius, while cesium melts at 28.5 degrees Celsius, so ununenium might continue the trend of lower melting points. Its boiling point is predicted to be about 630 degrees Celsius, quite close to francium's estimated 620 degrees Celsius, but a little lower than cesium's known value of 671 degrees Celsius. The density of ununenium is estimated to be somewhere between 3 and 4 grams per cubic centimeter. This continues the trend of increasing density as we move down the alkali metal group. Cesium has a density of about 1.93 grams per cubic centimeter, while francium is estimated at about 2.48 grams per cubic centimeter. When it comes to chemical behavior, ununenium should still act like an alkali metal, but with some important differences. It's expected to behave more like potassium or rubidium and less like cesium or francium. That's because relativistic effects make its outer electron more stable, reducing how reactive it is. Normally, we would expect ununenium to be extremely reactive, but instead, it might be less reactive than francium or cesium. Its main oxidation state will likely be +1, like all alkali metals. However, due to the way its outermost electrons are arranged, scientists think it might also be able to show a +3 oxidation state, which is not seen in any other alkali metal. This is caused by the instability and expansion of its 7p3 spinor, which makes some of the electrons easier to remove. Because some of ununenium's electrons from the 7p3 orbital may take part in bonding, many of its compounds are expected to have a strong covalent character. Francium shows a small amount of this too, like in francium superoxide. Because of this, ununenium may not be the most electropositive element, even though simple logic would suggest it should be. Instead, cesium likely keeps that title. Ununenium's electronegativity is thought to be close to sodium's value of 0.93 on the Pauling scale. The standard reduction potential of ununenium's UUE pair is predicted to be negative 2.9 volts, which is similar to that of francium and slightly above that of potassium. In the gas phase and at very low temperatures in the solid state, alkali metals can form diatomic molecules, where two metal atoms bond together. Normally, the bond lengths in these molecules grow longer as you go down the group from lithium to cesium. But ununenium breaks this pattern, forming a shorter bond due to the stabilization of its 8s orbital. Interestingly, the bond strength shows the opposite trend. It actually increases again for ununenium, and the UU bond might even be stronger than the KK bond. The enthalpy of sublimation, which tells us how much energy is needed to turn the solid metal into a gas, for ununenium is predicted to be about 94 kilojoules per mole compared to 77 kilojoules per mole for francium. In compounds like UAEF, ununenium fluoride, the bond is expected to have a strong covalent character. This is due to ununenium's high electron affinity, and because the bonding involves unusual orbitals like the 7p of ununenium and the 2p of fluorine. This kind of bonding is quite different from what we see in other S-block metals, or even in gold and mercury. The UEF bond is also expected to be stretched out because of a splitting in the 7p orbital, again caused by relativistic effects. A similar thing happens in other heavy element hydrides like astatine hydride, ATH, and tennessine hydride, TSH. Ununenium can also form a bond with gold, though this bond is predicted to be the weakest among all alkali metal gold bonds. Still, it would be stable enough to study. Based on this, scientists think the adsorption enthalpy, which tells us how strongly ununenium would stick to a surface, would be about 106 kilojoules per mole for gold, 76 kilojoules per mole for platinum, and 63 kilojoules per mole for silver. These are the smallest values among the alkali metals. The adsorption enthalpy for ununenium on Teflon is expected to be only 17.6 kilojoules per mole, which would be the lowest among all alkali metals. While the enthalpy of sublimation and the adsorption enthalpy tend to move in opposite directions as atomic number increases. These values help give scientists clues about how to isolate and study ununenium in the lab, possibly by watching how it behaves when placed on surfaces made of different metals. Scientists have long wondered if the periodic table, the chart that organizes all known chemical elements, might continue beyond what we already know. Right now, the element with the highest confirmed atomic number is called oganesson, which has the atomic number 118. This element finishes the 7th row, or period, of the periodic table. Any elements beyond this point are still purely imaginary. They haven't been discovered yet, either in nature or in a laboratory. If future scientists manage to create or find new elements beyond oganesson, they would be added to an 8th period. Just like the earlier periods, these new rows would help us see repeating patterns in the chemical properties of the elements. But this 8th period is expected to be even longer than the 7th because it's believed to include a whole new section of elements called the G block. This G block could contain at least 18 new elements, each with special electron patterns involving partially filled G orbitals. The idea of an 8th period with a G block was first suggested by famous American chemist Glenn Theodore Seaborg in the year 1969. According to this idea, the first element in the G block might be the one with atomic number 121. Scientists have already given it a temporary name, unbiunium. But despite many experiments and careful searches, no one has been able to create or detect these ultra-heavy elements so far. When scientists describe atoms using quantum mechanics, they use something called the orbital approximation, which helps explain how electrons are arranged. Based on this model, elements in the G block would have electrons in special G orbitals. However, as the atomic number gets very high, strange effects caused by Einstein's theory of relativity, called relativistic effects, start to interfere with this simple model. In other words, the rules that work for lighter elements start to fall apart for very heavy ones. Seaborg's model didn't take these relativistic effects into account, so it followed the same basic patterns seen in lighter elements. But later scientists, including Pekka Pykö and Burkhard Fricke, used powerful computer simulations to predict how elements might behave up to atomic number 172. They discovered that some of these new elements wouldn't follow the normal patterns of the periodic table. In fact, some were even predicted to break the famous Madelung rule, which helps determine how electrons fill up their orbitals. Because predictions about these new elements vary so much, scientists still haven't agreed on how to place them in the table. Another problem is that these super-heavy elements are expected to be extremely unstable. Most of them would probably decay almost instantly by releasing particles like alpha particles or splitting apart in a process called spontaneous fission. Still, there is hope. Scientists believe that a special island of stability might exist around element 126. This island could contain elements that last longer than usual, at least long enough to study them, because of certain protective effects inside their atomic nuclei. Some experts even think there could be another island of stability near element 164, though no one knows for sure how stable these future elements might be. It's also unclear just how far the periodic table can actually go. Will there really be a full 8th period? Could there even be a 9th period? No one knows. The International Union of Pure and Applied Chemistry, IUPAC, has a rule. An element officially exists only if it lasts longer than 10 femtoseconds. That's 100 trillionth of a second. That may sound incredibly short, but it's just enough time for an atom to form a cloud of electrons around its nucleus. As far back as the year 1940, some scientists pointed out that there could be a natural limit to how big atoms can get. A simple interpretation of the relativistic Dirac equation used in quantum physics suggests that neutral atoms might not be able to exist if the atomic number is greater than 137. This number comes from the reciprocal of a fundamental constant called the fine structure constant. Later studies, however, showed that the real limit might be a little higher, between atomic numbers 168 and 172. Beyond this, atoms might still exist, but only as bare nuclei without any surrounding electrons. These super-extreme atoms are called supercritical atoms. The idea of elements beyond uranium, called transuranic elements, dates back even earlier. In the year 1895, Danish chemist Hans Peter Jørgen Julius Thomsen predicted that uranium and thorium were part of a long row of 32 elements, ending in a chemically inactive one with an atomic weight around 292. That's surprisingly close to the actual weight of Oganessen's known isotope, which is about 294. In the year 1913, Swedish physicist Johannes Rydberg guessed that the next noble gas after radon would be element 118, and he even imagined heavier noble gases at atomic numbers 168, 218, 290, 362, and 460, right where modern rules would put them. Later, in the year 1922, the famous Danish physicist Niels Bohr predicted the electron structure of element 118 and suggested that we don't see elements beyond uranium in nature because they are too unstable. In the early 20th century, German scientist Richard Swin speculated that some of these elements could still exist, perhaps buried deep in the Earth's core, trapped in ancient meteorites, or frozen in the ice caps of Greenland. He even proposed the idea of longer-lived elements forming an island of stability. By the year 1955, scientists began calling these mysterious elements super-heavy elements. The first serious predictions about the properties of these elements came in the year 1957, when researchers explored the concept of nuclear shells, a bit like electron shells, but for protons and neutrons inside the nucleus. Around this time, the idea of an island of stability centered on element 126 became popular. In the year 1967, more advanced calculations suggested that the island might actually be centered around element 114, later named flerovium. This sparked a wave of interest in both creating and hunting for these elements. Throughout the 1970s, scientists searched for super-heavy elements in nature and tried to make them using particle accelerators. None were found at first, but gradually progress was made. As of April in the year 2022, scientists have tried to create every element up to number 127, except for element 123. The heaviest element ever successfully created was Oganessen in the year 2002. The most recently discovered one is called tennessine, found in the year 2010. To fit these super-heavy elements into the periodic table, Glenn Seaborg's model from 1969 introduced an eighth period, complete with the new G block and a group called the superactinides, starting at element 121. But again, his model didn't include relativistic effects, which we now know are crucial at high atomic numbers. In 1971, Burkhard Fricke calculated the table all the way up to atomic number 172 and found that some elements would behave very differently. Later studies, like one by Pekka Pirkko in the year 2010, confirmed that the usual periodic trends would not hold for many of these future elements. Right now, no one knows how far the periodic table can really go. While the known elements end at number 118, the increasing instability of heavier elements might limit how many more can exist. Glenn Seaborg himself once guessed that the periodic table might practically end around atomic number 120 due to nuclear instability. Before scientists officially discover a new chemical element, they give it a temporary name using a system created by the International Union of Pure and Applied Chemistry, or IUPAC for short. These placeholder names follow a strict pattern based on the element's atomic number. But in practice, scientists usually don't use these long, made-up names. For example, element number 164 technically has the placeholder name unhexquadium, with the symbol UQ. However, most people just call it element 164, and it's often written simply as 164 or E164. By the time we get to element 118, the last element currently confirmed, certain electron shells, or orbitals, are expected to be completely filled. These include the orbitals labeled 1s, 2s, 2p, all the way up to 7p. Scientists use a rule called the Aufbau principle to guess how the next elements might be arranged. According to this rule, the 8th row of the periodic table would begin filling the orbitals in this order: 8s, 5g, 6f, 7d, and 8p. However, starting after element 120, things become more complicated. The electron shells are so close together that it's hard to place the elements neatly into a table. Not all scientists agree on how the heavier elements should behave. In the year 1971, Burkhard Fricke and his team calculated the possible behaviors of elements all the way up to element 184. They noticed that many of the very heavy elements didn't follow the usual rules of orbital filling, like the Madelung rule. This happened because of something called relativistic effects, which become important when atoms are very heavy. These effects cause orbitals to overlap in strange ways, changing how electrons are arranged. Fricke's version of the periodic table focused more on the formal electron arrangements than on how the elements would actually behave in chemical reactions. For example, he placed elements numbered 156 through 164 in groups 4 through 12. This is because their electron configurations included the 7d orbitals, from 7d2 to 7d10. However, unlike earlier transition metals, these new elements wouldn't use the 8s electrons in bonding. Instead, the 9s orbital would come into play. Because of this, element 164, with a configuration of 7d10 and 9s0, behaves similarly to palladium, which has a configuration of 4d10 and 5s0. Fricke suggested that elements 157 to 172 might resemble elements in groups 3 through 18, though he wasn't sure exactly where to place elements 165 and 166. They might be more like group 1 and 2 elements, or more like group 11 and 12 elements. In the end, he put elements 157 through 164 into groups that weren't quite perfect matches for their chemical behavior. In 2006, scientists named Nefedov, Trzaskovskaya, and Yargemsky also looked into these heavy elements. They agreed with Fricke's general ideas and studied elements up to 164. They compared these new elements to existing transition metals from the 5th period of the periodic table. For example, element 159 has the electron configuration 7d4 and 9s1, like niobium, which is 4d4 and 5s1. Element 160 has 7d5 and 9s1, like molybdenum, with 4d5 and 5s1. Element 162 is 7d7 and 9s1, like ruthenium, with 4d7 and 5s1. Element 163 is 7d8 and 9s1, like rhodium, with 4d8 and 5s1. Element 164 is 7d10 and 9s0, just like palladium, with 4d10 and 5s0. So, while Fricke placed some elements in not quite right groups, Nefedov and his team actually placed each element where its chemical behavior made the most sense. In their work, they also pointed out that some super-heavy elements, like roentgenium and copernicium, have unusual electron configurations compared to gold and mercury. These differences were marked with special asterisks. Still, they believed that copernicium probably behaves very much like mercury. In 2011, a Finnish chemist named Pekka Pika used powerful computer models to explore elements up to atomic number 172. He agreed with Fricke's ideas about orbital order, but offered an improved table. He suggested that elements from 121 to 164 could be organized better if we looked at how they behave when they form ions. To keep track of how electrons were arranged, Pika had to move some elements out of numerical order. For example, he placed elements 139 and 140 in groups 13 and 14 because their 8p½ orbitals needed to be filled. He also separated the 5G, 8p½ and 6f series. Fricke and Nefedov didn't break up the series like this in their work. Later on, another scientist named Andrei Kulsha built on these earlier studies. He came up with two new versions of the extended periodic table that reached up to element 172. These tables refined the ideas of Nefedov and were influenced by Pika's work. Both versions placed elements from 157 to 172 as part of the 8th period and matched them with earlier elements from yttrium to xenon, which are found in the 5th period. This continued the pattern that Nefedov used for elements 157 to 164, comparing them to elements from yttrium to palladium. It also agreed with Fricke's ideas about their chemical behavior. Kulsha also proposed two different ways to arrange the elements from 121 to 156, which don't have clear matches in earlier parts of the table. In his first version, created in 2011, he grouped elements 121 to 138 and 139 to 156 into two rows. These were called the ultransition elements because they added a 5G18 subshell into their electron structure. Based on their oxidation states, the first group behaved like the lanthanides and the second like the actinides. In his second version, published in 2016, he created a G block of elements from 121 to 142 and placed elements 143 to 156 into an F block under actinium to nobelium. This means that the 8th period of the periodic table could contain as many as 54 elements. According to this model, the next noble gas after oganesson, which is element 118, would be element 172. In the year 2023, 5 scientists, Smits, Dulman, Indelicato, Nazarevich, and Schwerdtfeger, tried once again to figure out where elements from 119 to 170 should be placed in the periodic table. They based their ideas on electron configurations, but some elements, like 121 to 124 and element 168, didn't fit perfectly. In their model, element 145 showed up in 2 places. Some spots were occupied twice, and other spots were left empty. Scientists have also tried to create some of these new elements in labs. They've attempted to make all period 8 elements up to unbiseptium, except for unbitrium, but so far, none of these attempts have succeeded. Right now, scientists are still trying to create element 119, also known by its placeholder name, ununenium. The first time anyone tried to make element 119 was in the year 1985. Researchers bombarded a target of Einsteinium-254 with calcium-48 ions at an accelerator in Berkeley, California. Unfortunately, they didn't detect any atoms. The experiment showed that the likelihood of success, the cross-section, was less than 300 nanobarns. Later studies suggested that the actual chance of success might be 600,000 times lower than that, at just half a picobarn. Between April and September, in the year 2012, scientists at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany, carried out a fascinating experiment. Their goal was to create 2 new super-heavy isotopes, one called isotope 295 of element 119 and another called isotope 296 of the same element. To do this, they bombarded a rare and radioactive substance called berkelium-249 with a beam of titanium-50 atoms. According to theoretical predictions, the scientists believed they might be able to produce at least one atom of the mysterious element 119, also known by the temporary name ununenium, within 5 months. Interestingly, because berkelium-249 slowly turns into another element, californium-249, over time, it has a short half-life of only 327 days. This experiment also gave them a chance to search for element 120 at the same time. Originally, the experiment was scheduled to run until November of that year. However, it was cut short because the same berkelium target was needed for another important purpose, confirming the discovery of another rare element called tennessine. For that task, they switched to using calcium-48 projectiles instead. Among the many possible combinations of atoms, the scientists had high hopes for the reaction between berkelium-249 and titanium-50. This pairing was considered the most promising practical way to create element 119 because of its asymmetry, meaning the two types of atoms were quite different in size and shape, which often increases the chances of successful fusion. It was also a relatively cold reaction, meaning it didn't involve as much energy, which can help the newly formed atoms survive long enough to be detected. Though an even better reaction involving einsteinium-254 and calcium-48 was known, it was almost impossible to carry out because preparing even a small amount of einsteinium is extremely difficult. But the switch from calcium-48, sometimes called the silver bullet of element making, to titanium-50 came with a cost. Titanium's heavier mass and different properties reduced the likelihood of creating element 119 by about 20 times. This is because the success of such reactions heavily depends on how asymmetrical the two colliding atoms are. Because the scientists expected the new atoms to exist for only a very short time, perhaps just a few millionths of a second, they used incredibly fast electronics to detect their fleeting appearance. Despite their efforts, no atoms of element 119 were found. This suggested that the probability of creating such an atom, known as the cross-section, was lower than 70 femtobarns. A femtobarn is a unit used to measure these probabilities. In fact, calculations showed the real chances might be as low as 40 femtobarns, which is right at the edge of what today's technology can detect. A few years later, in January of the year 2018, another team of scientists in Waco, Japan, at the Riken Research Institute, began their own attempt to find element 119. They used a different combination, bombarding curium-248 with a beam of vanadium-51. Curium was chosen as the target instead of heavier elements like berkelium or californium, mainly because it is easier to prepare. The curium came from the Oak Ridge National Laboratory in the United States, and Riken built a powerful beam of vanadium ions for the job. This experiment started in a cyclotron, while Riken's larger accelerator systems were being upgraded. The upgrades were completed in the year 2020. Today, the experiment continues for at least 100 days each year, with the hope that they will someday detect even a single atom of the elusive element. Interestingly, this work is being supported by funding from the Emperor of Japan. Meanwhile, in Russia, scientists at the Joint Institute for Nuclear Research, also known as JINR, have plans of their own. They hope to create element 119 by combining americium-243 with chromium-54. While they haven't shared an exact timeline, their intentions remain clear. Back in the year 2006, the same Russian team successfully created the heaviest known element at the time, oganesson, by smashing californium-249 with calcium-48. Inspired by this success, they launched new experiments in March and April of the following year, 2007, this time aiming to make element 120, also called unbenillium. They used iron-58 and plutonium-244 for their experiment. However, none of the new atoms were observed. The cross-section, or the chance of success, was found to be less than 400 femtobarns. The Russian team decided to improve their equipment before trying again. Around the same time, in April 2007, the German team at GSI also attempted to make element 120 using uranium-238 and nickel-64. But once again, no new atoms were found. Their results showed that the probability of success was below 1.6 picobarns. A picobarn is 1,000 femtobarns. Undeterred, the Germans repeated the experiment 3 more times. In April to May 2007, January to March 2008, and again in September to October of the same year. All these attempts failed to produce element 120, setting a new cross-section limit of 90 femtobarns. Later, in the years 2010 and 2011, the GSI team tried a different reaction, using more radioactive materials and a more asymmetrical setup. This time, they hoped that the change would make it 5 times more likely to create the new element. Surprisingly, they saw 3 signals that matched what they expected from the decay of isotope 299 of element 120, as well as its decay products, oganesson 295 and livermorium 291. But the decay times were longer than predicted, and no firm conclusions could be drawn. Another attempt was made in August to October 2011, using an even more asymmetrical reaction. That same setup was tried again the following year during the attempt to make element 119. Because berkelium-249 eventually decays into californium-249, it offered another opportunity to try different fusion combinations. The most promising setup for creating element 120 was believed to be californium-249 combined with titanium-50. However, no atoms were detected, setting an upper limit of 200 femtobarns for the reaction's cross-section. According to the German scientist Jens Volker Kratz, the actual chances of making element 120 might be even lower, around 0.1 femtobarn. For comparison, the record for the smallest successful cross-section so far is 30 femtobarns, achieved in the creation of the element nihonium using bismuth 209 and zinc 70. Kratz also estimated that the best chance for element 119 is about 20 femtobarns. If these predictions are right, then making element 119 is already close to the limits of what scientists can currently do. As for element 120, it may only become possible if completely new and more advanced methods are developed. In May of the year 2021, the Russian team at JINR announced their plan to try creating element 120 using the californium-249 and titanium-50 reaction. However, this required a special target to be made by the Oak Ridge National Laboratory in the United States. After the Russian invasion of Ukraine in February 2022, international cooperation with Russian institutes came to a halt due to global sanctions. Because of this, JINR has now decided to try a different approach, using curium-248 and chromium-54. In late 2023, they tested this method by successfully creating livermorium-288 using uranium-238 and chromium-54. If all goes well, their first full experiments to create element 120 may begin as early as the year 2025. Starting in the year 2022, scientists began making plans to use the 88-inch cyclotron at the Lawrence Berkeley National Laboratory, LBNL, located in Berkeley, California, in the United States. Their goal was to create new, never-before-seen elements by firing a specific type of atomic particle, titanium-50, at heavier elements. The first test involved smashing titanium-50 particles into plutonium-244. This reaction was successful. It created 2 atoms of a very heavy element called livermorium, with a mass number of 290 in the year 2024. Because this worked, the scientists are now planning a much more ambitious experiment. In the year 2025, they will try to make a brand new element, element 120 by bombarding californium-249 with titanium-50. This effort will be a collaboration between two major laboratories, the Lawrence Berkeley National Laboratory and the Lawrence Livermore National Laboratory, LLNL, which has previously worked closely with the Joint Institute for Nuclear Research, JINR, in Russia. Going back in time, the very first attempt to create element 121, known as unbiunium, was made in the year 1977. At that time, researchers tried smashing copper-65 ions into uranium-238 at a facility in Germany called the Gesellschaft für Schwerionenforschung, or GSI for short. Even earlier, in the year 1972, the first efforts to create element 122, called unbibium, were carried out by a team led by Flerov at the Joint Institute for Nuclear Research, JINR. They used a type of experiment known as hot fusion, where very heavy atomic nuclei are made to collide at high energies. These early experiments were driven by the idea that there might be a special region on the periodic table, often called the island of stability, where super-heavy elements would last longer because of the perfect number of protons and neutrons in their nuclei. In this case, the predictions focused on a neutron number of 184 and proton numbers higher than 120. Unfortunately, no new atoms were found in those first experiments. The best they could measure was a production rate, or yield, of 5 nanobarns, which equals 5,000 picobarns. Later research showed that their equipment simply wasn't sensitive enough, by at least a factor of 1,000. In the year 2000, the GSI Center in Germany repeated the experiment, but this time using much more advanced and sensitive technology. Even so, creating these extremely heavy elements remains very difficult. To have a real chance at success, scientists say they will need to increase the sensitivity of their experiments to just 1 femtobarn. That's 1/1,000,000th of a nanobarn. Another attempt to create element 122 happened in the year 1978. Scientists bombarded a natural sample of the element erbium with ions of xenon-136. They expected this would result in atoms that would decay in stages, possibly ending with isotopes of flerovium, another super-heavy element, which was thought to be near the center of the island of stability. After 12 hours of continuous bombardment, however, no atoms were detected. That, along with a similar failed attempt to make element 121 using uranium-238 and copper-65, led scientists to believe that these super-heavy elements either fall apart in less than 1 microsecond or are produced in incredibly tiny amounts. Later research confirmed that both ideas were likely true. Back in the early 1970s, these first experiments were also motivated by the idea that some super-heavy elements might even exist naturally on Earth, though we now know that's probably not the case. Between the years 2000 and 2004, the Flerov Laboratory of Nuclear Reactions conducted several experiments to study how super-heavy atomic nuclei split or undergo fission. They used 2 different reactions: curium-248 combined with iron-58 and plutonium-242 combined with nickel-64. Their results showed that these giant nuclei tend to break apart by emitting stable chunks, especially tin-132, which has 50 protons and 82 neutrons, a so-called doubly magic nucleus. They also noticed that whether the experiment used calcium-48 or iron-58 projectiles, the overall outcome was similar, which could make iron-58 a useful material in future super-heavy element experiments. In the year 2006, scientists at the Grand Accélérateur National Dion-Lourdes, GANIL, in France, tried something even more ambitious. They aimed to investigate elements with atomic numbers of 114, 120, and 124. They bombarded germanium with uranium ions to see how the compound nuclei would behave. Their findings, published in full in 2008, revealed something fascinating. The compound nuclei stayed together for longer than 10 to the power of -18 seconds, suggesting a stabilizing effect near atomic number 124. This shifted scientists' focus to higher atomic numbers for the next stable magic proton number, moving past earlier assumptions that the next stable shell was at 114. These compound nuclei are basically temporary blobs of protons and neutrons that have not yet arranged themselves into a stable structure. According to the International Union of Pure and Applied Chemistry, IUPAC, an atom needs to exist for at least 10 to the power of negative 14 seconds to be considered a real nuclide, and anything shorter doesn't count as a discovery. Also, in 2006, at the Legnaro National Laboratories in Italy, researchers repeated a similar fission study using the compound nucleus of element 124. Again, they found that the nuclei tended to break into parts like tin-132, just like in earlier experiments. They also observed that the heavier the nucleus, the more neutrons it emitted during fission, supporting a long-standing trend seen in nuclear physics. The only recorded attempt to make element 125, called unbipentium, took place between 1970 and 1971 in Dubna, Russia. In that experiment, scientists bombarded americium-243 with zinc ions. Sadly, no atoms were observed, and the limit of detection was again 5 nanobarns. At the time, researchers hoped that elements with around 126 protons and 184 neutrons might be especially stable, but more recent studies suggest that stability may peak at lower atomic numbers, such as copernicium, element 112. The only known attempt to create element 127, named unbiseptium, happened in the year 1978 at the GSI facility in Germany. There, xenon-136 ions were fired at a tantalum target. Just like many earlier efforts, this experiment was also unsuccessful. Back in the year 1976, a group of American scientists from different universities came up with a bold idea. They suggested that certain mysterious and extremely heavy elements, called primordial superheavy elements, might be hiding in nature and could be responsible for unexplained radiation damage found in some minerals. These elements included livermorium and some hypothetical ones with atomic numbers 124, 126, and 127. The damage they referred to included strange marks known as radio halos, which puzzled researchers for years. This theory sparked excitement in the scientific community, and many researchers began searching for these hidden elements in natural materials between the years 1976 and 1983. One of the most well-known efforts was led by Professor Tom Cahill from the University of California at Davis. In 1976, he and his team claimed they had found alpha particles and X-rays with exactly the kind of energy needed to explain the strange radiation damage. This, they said, was proof that super-heavy elements might really exist in nature. They specifically believed that long-lasting versions, called long-lived nuclei, of elements 124 and 126 could have survived for about 1 billion years and were present in tiny amounts, about 1 part in 100 billion, compared to familiar heavy elements like uranium and plutonium. However, not everyone agreed. Other scientists questioned the evidence and doubted the idea that these super-heavy elements even existed. They pointed out that in order for such elements to be stable for so long, they would need a special internal structure, like a closed shell of neutrons, at either 184 or 228 neutrons. Unfortunately, the versions of livermorium and the other elements that could have this structure would either be unstable or would decay too quickly to be found in nature. To make things even more confusing, some scientists thought the strange radiation might not come from super-heavy elements at all. They suggested it could be caused by nuclear changes happening inside cerium, a naturally occurring element. This added even more uncertainty to the whole idea. Then, years later, on April 24, 2008, another team of researchers led by Professor Amnon Marinoff from the Hebrew University of Jerusalem made a dramatic claim. They said they had discovered single atoms of a mysterious element with atomic number 122, which some call unbibium, in naturally occurring thorium samples. They believed it existed in amounts as small as 1 part in a trillion. Marinoff's team said these atoms were special versions called super-deformed or hyper-deformed isomers that could live for at least 100 million years. However, their discovery didn't go unchallenged. Some scientists criticized the methods they used, saying the same techniques had led to doubtful results in the past. Even the scientific journals Nature and Nature Physics refused to review their article. In 2008, a criticism of their method was published in Physical Review C, a respected scientific journal. Marinoff's group wrote a rebuttal and had it published, but doubts remained. Later, a much more sensitive technique called accelerator mass spectrometry, AMS, was used to try to repeat Marinoff's experiment. Despite being 100 times more sensitive, it failed to find any sign of the super-heavy element. This greatly weakened the credibility of the original claim, and similar doubts were raised about their earlier suggestions of finding unusual versions of thorium, roentgenium, and element 122. While it is still remotely possible that tiny traces of unbibium exist in thorium samples, it now seems very unlikely. As for whether primordial super-heavy elements exist on Earth today, no one really knows for sure, even if they were once present and caused strange radiation damage in the distant past. They may have since decayed into nothing or disappeared completely. There's another reason scientists are skeptical. The natural process believed to form heavy elements, known as the R process, is expected to stop working around mass numbers 270 to 290. This would mean elements heavier than 120 might not form naturally at all. Interestingly, one modern theory tries to explain the strange light spectrum of a star called Przybylski's star by suggesting that natural versions of flerovium, element 114, and another unknown element, element 120, might exist there. Currently, the heaviest element ever made in a lab is element 118, called oganesson. The next elements, numbers 119 and 120, have not yet been created, but scientists predict that they will start a new row, or period, in the periodic table. Element 119 is expected to behave like an alkali metal, and element 120 like an alkaline earth metal, similar to rubidium and strontium, rather than their heavier cousins francium and radium. After element 120, a whole new family of elements is expected to begin, the superactinides. These would fill unusual electron orbitals like 5G, 6F, and 7D, making their chemistry much more complicated. In fact, beyond element 122, no one has been able to do complete and accurate calculations because the electronic structures become so tangled and strange. The first two elements in this superactinide group, element 121, called unbiunium or eka-actinium, and element 122, unbibium or eka-thorium, are expected to act like actinium and thorium, but with some key differences in their electron shells. Unbiunium's first ionization energy, the energy needed to remove an electron, is predicted to be even lower than that of any known element except the alkali metals, making it extremely reactive. Element 122, unbibium, should behave similarly to thorium, with a usual charge of +4, but with a different electron structure that makes it easier to ionize than thorium. The orbital known as 5G is expected to begin filling around element 125, also called unbipentium or eka-neptunium. As more electrons are added in these superactinides, their outermost electrons may be held so loosely that they can be removed easily. For example, unbihexium, element 126, might reach a whopping +8 oxidation state, and maybe even higher. It might also form unusual compounds like a stable fluoride, 126F, where its 5G orbital bonds directly with fluorine's 2p orbital. This element might also have oxidation states of +2, +4, and +6, but +4 would likely be the most common. The elements from 125 to 129 could also form hexafluorides, compounds with 6 fluorine atoms, though some of these would be weakly bound. By the time we get to element 129, the chemical bonding might become much stronger, shifting from ionic to more covalent types of bonds involving those strange 8p orbitals. All in all, these predicted super-heavy and superactinide elements may have wild and surprising chemical properties, far beyond what we're used to with regular elements. If scientists ever manage to create or find them in nature, they could open the door to an entirely new and mysterious chapter in chemistry. Even though some of the early superactinide elements may be able to reach very high chemical oxidation states, meaning they can lose many electrons during chemical reactions, scientists have predicted that removing electrons from the 5G orbitals, a type of electron cloud around the nucleus, will be very difficult. For example, the ions of elements numbered 1256 and 1267 are expected to have a 5G1 electron setup. This is similar to the 5f1 configuration seen in the Neptunium 6+ ion. This behavior is quite similar to what we see with the lanthanide elements, where the 4f electrons do not participate much in chemical reactions. The reason for this lies in how the 5G orbitals are shaped. They are small and buried deep inside the atom's electron cloud, making them hard to reach or affect chemically. Interestingly, the 5G orbitals do not appear in the natural electron arrangements of any element we know today. Because of that, scientists believe that if superactinides contain electrons in these orbitals, they might create brand new types of chemical bonds, known as hybrid orbitals. These unique bonds could affect how these exotic elements behave, but since we have never observed G electrons in known elements, predicting their chemistry is a real challenge. As we move further down the superactinide series, scientists believe that the elements will generally become less reactive and have lower oxidation states. By the time we reach element 132, its most stable oxidation state is expected to be only +6. For element 144, this drops further to +4 or even +3. At the very end of the series, these elements may only show a +2 state, or possibly no oxidation state at all, because the 6f orbital, which is being filled, lies too deep inside the atom to participate in chemical reactions. The 8s and 8p½ electrons are also tightly held by the atom and won't easily take part in reactions either. It is expected that the 5G shell will be filled by element 144, and the 6f shell will be completed by around element 154. Around this region, the 8p½ electrons are so strongly bound that they are no longer chemically useful. That means very few electrons are available to react with other elements. According to calculations by a scientist named Fricke and his team, by the time we reach element 154, the 6f shell is completely filled, and no other useful orbitals extend beyond the inactive 8s and 8p½ electrons. This could make element 154 as unreactive as a noble gas. However, other researchers like Pekka Paikka think that element 155 might still be able to lose electrons from the 6f shell. For example, the 3+ ion of element 155 should have a full 6f shell, and its fourth ionization energy, the energy needed to remove the fourth electron, would be similar to that of terbium or dysprosium, both of which are known to reach the +4 state. Much like what happens in the lanthanide and actinide series, scientists predict a superactinide contraction, a slow shrinking of the atom's sizes as we go from one element to the next in the series. In the lanthanides, this contraction is about 4.4 picometers per element. In the actinides, it's about 3 picometers per element. This size shrinking happens because the electrons in the f orbitals are pulled closer to the nucleus as more protons are added. In the superactinides, the contraction is slightly smaller, about 2 picometers per element, but its overall effect is even greater. That's because in the superactinides, there are 32 electrons filling the deep 5G and 6F shells, compared to only 14 in the lanthanides, 4F, or actinides, 5F. Pekka has grouped the superactinides into three parts: a 5G series from elements 121 to 138, an 8p½ series from elements 139 to 140, and a 6F series from 141 to 155. He points out that the energy levels of these orbitals overlap a lot, and so, in the early superactinide elements, we might also see electrons in 6F, 7d, or 8p½ orbitals. He believes that the 5G electrons will not be very active in chemical reactions, just like how only 1 or 2 4F electrons are usually involved in the chemistry of the lanthanides. He also predicts that very high oxidation states, possibly even as high as +12, might appear in the 6F series, especially around element 148. Another scientist, Andrei Kulsha, has called elements 121 to 156 the ultransition elements. He suggests splitting them into two groups of 18. The first group, from element 121 to 138, would resemble the lanthanides, with oxidation states between +4 and +6, and very similar chemistry due to the filling of the 5G shell. The second group, from element 139 to 156, would be more like the actinides. In this second group, the elements in the early 140s might show very high oxidation states as the 6F shell becomes more important, but later elements would have lower oxidation states. By the 150s, the 8p½ electrons become chemically inactive. Since the two rows are separated by the filling of the complete 5G18 shell, they may mirror each other in structure. Take element 156, for example. It is expected to usually exist in the +2 oxidation state. This is because it has two loosely held 7d electrons above a very stable inner core, which includes a full 5G18 and 6f14 arrangement, as well as tightly held 8s and 8p½ electrons. This makes it similar to nobelium, which also has two easily removed 7s electrons above a full 5f14 core and is normally found in the +2 state. Element 156 is expected to have an ionization energy, the energy required to remove an electron, of about 400 kilojoules per mole and a metallic radius of about 170 picometers. It would be a very heavy metal with a predicted atomic mass of around 445 atomic units and an extremely high density of around 26 grams per cubic centimeter. Elements 157 to 166 are expected to be the 7d transition metals in period 8. In these elements, the 8s and 8p½ electrons are so strongly held that they won't participate in reactions. However, the 9s and 9p½ orbitals are expected to be available for forming chemical bonds. These transition metals are predicted to resemble the 4d elements, like yttrium through cadmium. For instance, element 164 is expected to have a 7d10 9s0 electron configuration, very much like palladium, which has a 4d10 5s0 setup. But unlike palladium and other noble metals that don't react easily, these new transition metals are not expected to be quite as noble. That's because they lack an outer s electron shell for protection, and because the 7d orbitals are split into two uneven energy levels due to a phenomenon called relativistic effects. This causes their first ionization energies to be lower than those of their lighter counterparts. One particularly exciting element is unhexquadium, which is element 164. Scientists are very interested in it because theoretical models suggest that some of its isotopes, especially those with 308 or 318 neutrons, might lie at the center of a second island of stability. The first island of stability is believed to exist around copernicium, particularly the isotopes with mass numbers 291, 293, and 296, which may have half-lives of hundreds or even thousands of years. Calculations show that the 7d electrons in unhexquadium should take part in chemical reactions quite easily. This means that in addition to its usual +2 state, it could also form stable +4 and +6 oxidation states in water, especially when strong ligands, molecules that attach to metals, are present. It might form compounds like unhexquadium tetracarbonyl, unhexquadium tetrafluorophosphine, or even unhexquadium dicyanide, compounds with similar shapes and structures to those formed by palladium. This kind of chemical activity is very different from that of lead, which unhexquadium would normally be grouped with on the periodic table, except that relativistic effects drastically change its behavior. Still, unhexquadium in the +2 state would behave more like lead, while in the +4 or +6 states it would act very differently. Unhexquadium is expected to be a soft Lewis acid, a term describing how it accepts electrons, with a softness parameter of about 4 electron volts. It should have a first ionization energy around 685 kilojoules per mole, similar to molybdenum, and a surprisingly small metallic radius of 158 picometers. That is almost the same as magnesium, even though unhexquadium's atomic mass is about 474 atomic units, more than 19 times heavier than magnesium. Because it is both very heavy and very small, unhexquadium is predicted to be extremely dense, around 46 grams per cubic centimeter. That's more than twice the density of osmium, which is currently the densest element known. In fact, only unhextrium, its neighboring element numbered 163, is predicted to be even denser, at 47 grams per cubic centimeter. Unhexquadium should have very strong chemical bonds in its solid metallic form, which would give it a high melting point. As a metal, it is expected to be quite noble, similar to palladium and platinum, and might even show some chemical similarities to oganesson, the heaviest noble gas. Both unhexquadium and oganesson have similar ionization energies and full electron shells. However, while oganesson would be a poor noble gas due to its weak chemical inactivity, unhexquadium is expected to be a very good noble metal. Elements 165, unhexpentium, and 166, unhexhexium, the final two metals in the 7th D block, are expected to act similarly to the alkali and alkaline earth metals when they are in the +1 and +2 oxidation states, respectively. The 9 s electrons of these elements will have ionization energies similar to those of the 3 s electrons of sodium and magnesium. This is due to relativistic effects, which cause the 9 s electrons to be much more tightly bound than non-relativistic calculations would suggest. Normally, elements 165 and 166 should show the +1 and +2 oxidation states, but the ionization energies of the 7d electrons are low enough to allow for higher oxidation states. For example, element 165 could also form a +3 oxidation state, though element 166 is unlikely to form a +4 oxidation state. This creates a situation similar to the lighter elements in groups 11 and 12 of the periodic table, particularly gold and mercury. Like mercury, but not copernicium, ionization of element 166 to form the ion 166 2+ is expected to lead to a 7d10 configuration. This would correspond to the loss of the s electrons, but not the d electrons, making element 166 more similar to the lighter, less relativistic group 12 elements like zinc, cadmium, and mercury. The next 6 elements, numbered 167 through 172, are expected to be the last main group elements in their period and to share similarities with the 5 p elements indium through xenon. For elements 167 to 172, the 9 p1/2 and 8 p3/2 shells will be filled. These energy levels are so close together that they will act as one combined p subshell, much like the non-relativistic 2p and 3p subshells. As a result, the inert pair effect does not occur in these elements. The most common oxidation states for elements 167 through 170 are expected to be +3, +4, +5, and +6, respectively. Element 171, unseptunium, is expected to show similarities to the halogens, with oxidation states ranging from -1 to +7, but its physical properties will be closer to those of a metal. Its electron affinity is predicted to be 3.0 electron volts, allowing it to form a compound like H171, similar to hydrogen halides. The 171 negative ion is expected to behave as a soft base, similar to iodide, I negative. Element 172, unseptobium, on the other hand, is expected to behave like a noble gas, with properties similar to xenon. The ionization energies of xenon, 1170.4 kilojoules per mole, and element 172, 1090 kilojoules per mole, are predicted to be very similar. However, element 172 will likely be a liquid or solid at standard temperature and pressure due to its much higher atomic weight. It is also expected to be a strong Lewis acid, forming compounds like fluorides and oxides, much like its lighter counterpart, xenon. Because of the similarities between elements 165 to 172 and the second and third periods of the periodic table, some scientists, including Fricker and others, have suggested that these elements could form a ninth period, with the eighth period ending at element 164. This ninth period would be similar to the second and third periods in that it would have no transition metals. However, this analogy is not perfect for elements 165 and 166. While these elements do begin a new S shell, 9s, they are still above a D shell, making them more chemically similar to the elements in groups 11 and 12. Beyond element 172, there is potential to fill several additional electron shells, including the 6G, 7F, 8D, 10S, and 10p1/2 shells. These electrons would be very loosely bound, which could lead to extremely high oxidation states. However, as the ionic charge increases, these electrons are expected to become more tightly bound. As a result, there is likely to be another long transition series similar to the superactinides. In element 173, unseptrium, the outermost electron could enter one of several subshells, such as the 6G7/2, 9p3/2, or 10s subshells. Due to the spin-orbit interactions, a very large energy gap is expected between these and the 8p3/2 subshell. As a result, the outermost electron will be very loosely bound and easily lost, allowing the formation of a 173+ ion. This would make element 173 behave chemically like an alkali metal, possibly more reactive than even cesium. The ionization energy for element 173 is predicted to be 3.070 electron volts, compared to cesium's known value of 3.894 electron volts. Element 174, unseptquadium, may add an 8d electron and form a stable 174 2+ ion. Its ionization energy is predicted to be 3.614 electron volts. Element 184, unoctquadium, was a focus of early predictions because it was initially thought to represent a proton magic number. It is expected to have an electron configuration of 6G5, 7F4, 8D3, with at least the 7F and 8D electrons being chemically active. Its chemical behavior is expected to resemble that of uranium and neptunium. Further ionization past the +6 state, removing the 6G electrons, is thought to be unprofitable. The +4 oxidation state is expected to be the most common in aqueous solutions, with +5 and +6 being possible in solid compounds. In the world of nuclear physics, there's a fascinating idea called the island of stability. This isn't a real island, of course. It's a term scientists use to describe a special group of super-heavy elements that might last much longer than other heavy elements we've discovered so far. Most of the super-heavy elements we've made only stick around for a few seconds or less before falling apart. But in this imaginary island, some isotopes might survive for minutes, days, or even millions of years, which is a huge deal in nuclear science. Scientists imagine this island appearing on something called the chart of Nuclides, a kind of map that shows all the known combinations of protons and neutrons in atomic nuclei. The island would be separated from the more stable elements we know naturally exist, kind of like a mysterious land far from familiar shores. The reason scientists think such an island might exist has to do with what they call magic numbers. These are specific numbers of protons and neutrons that make a nucleus much more stable. Think of them as perfect combinations. Just like certain numbers of bricks can make a strong wall, certain numbers of protons and neutrons can make a very stable nucleus, even in very heavy elements. Experts believe that this island of stability might be found around elements like copernicium and flerovium, especially when there are about 184 neutrons in the nucleus. This number is predicted to be a magic one for neutrons, and when combined with the right number of protons, especially around element 114, flerovium, the nucleus might resist breaking apart for much longer than usual. In fact, the stabilizing effects might extend to nearby elements as well, and some scientists even suspect there could be other, smaller islands of stability further out, especially for what are called doubly magic nuclei, those with magic numbers of both protons and neutrons. While many scientists predict these longer-lived isotopes might last minutes or days, some more hopeful researchers imagine that a few could survive for millions of years. That would be incredible. Long enough to maybe find them in nature, or use them for advanced technologies we haven't even thought of yet. The idea of magic numbers and the nuclear shell model goes back to the 1940s. But despite this idea being around for so long, we haven't actually found any of these long-lived super-heavy isotopes. None have ever been discovered naturally, and all of the super-heavy elements we know had to be made by scientists in labs through complicated nuclear reactions. Unfortunately, creating the right kind of reaction to reach the heart of the island of stability has proven to be very tricky. We might need to invent entirely new kinds of reactions to make it happen. Even so, scientists have made great progress. They've successfully created super-heavy elements all the way up to element 118, called oganesson, which contains up to 177 neutrons. These experiments already show a bit of increased stability around elements like element 110 to element 114, giving researchers hope that the island of stability really does exist, and we are getting closer to reaching it. To understand how this all works, you need to know a few basics. Every atomic nucleus is made up of protons and neutrons. The number of protons, called Z, or atomic number, decides which element it is and where it belongs on the periodic table. The total number of protons and neutrons is called the mass number, A. Scientists have identified around 3,300 different combinations of these particles, known as nuclides. They organize these nuclides on a special chart with the number of protons on one axis and the number of neutrons on the other. This chart also shows how long each radioactive nuclide lasts before decaying. As of the year 2019, there were 251 nuclides considered stable, meaning they've never been observed to decay. Interestingly, as the number of protons in an atom increases, it usually needs more neutrons to stay stable. The heaviest element with a stable isotope is lead, which has 82 protons. Beyond that, elements become more unstable, especially after curium, which has 96 protons. A nucleus's stability depends on its binding energy, how tightly all the particles are held together. The more binding energy per particle, the more stable the nucleus. This energy tends to increase up to about mass number 60, then gradually goes down. If a nucleus can split into two smaller parts that have lower total energy, it becomes unstable. While quantum mechanics allows such a split to happen through a process called quantum tunneling, the chances increase if the nucleus is very heavy or imbalanced in its number of protons and neutrons. Protons in the nucleus naturally push away from each other because they all carry a positive charge. Neutrons don't have a charge, but they help hold the nucleus together by balancing out this repulsion. As scientists began creating artificial elements heavier than uranium, they noticed that these nuclei got more unstable as they got heavier. Some even wondered if there might be a natural end to the periodic table. When scientists discovered plutonium, element 94, they almost named it ultimium, thinking it might be the last element ever found. By the time the 1930s rolled around, scientists were already guessing at the limits of how heavy an element could be. In 1939, some experts thought element 104 might be the heaviest we could ever make. Later, in the 1960s, this prediction was extended to element 108. But the dream of reaching beyond those limits didn't fade. Back in 1914, a German physicist named Richard Swin wondered if super-heavy elements with atomic numbers around 108 might exist in space and be part of the mysterious radiation coming from cosmic rays. In 1931, he suggested that elements heavier than uranium, maybe around atomic numbers 100 or 108, might even be long-lived enough to exist naturally. Later, in 1955, American physicist John Archibald Wheeler supported the idea, and by 1958, he and Frederick Werner introduced the term super-heavy element in a scientific paper. Still, the idea didn't catch on until about a decade later, when scientists improved the nuclear shell model. This model compares the structure of an atomic nucleus to the layers of an onion or the shells of electrons in atoms. Inside the nucleus, protons and neutrons fill up shells. Once a shell is filled, it takes much more energy to add another particle. When both the proton and neutron shells are full, the nucleus becomes especially stable. This model was developed in the 1930s, but it was not until 1949 that German physicists Maria Goeppert-Mayer and Johannes Hans Daniel Jensen independently came up with the correct version. For this, they both won the Nobel Prize in Physics. The specific numbers of particles that complete these shells are called magic numbers. So far, scientists have found that 2, 8, 20, 28, 50, 82, and 126 are magic numbers for neutrons, and protons share most of these same numbers. The next predicted magic number for neutrons is 184. When both the protons and neutrons in a nucleus have magic numbers, the nucleus is called doubly magic and tends to be even more stable than usual. Examples include oxygen-16, tin-132, and lead-208. In the late 1960s, physicists began developing more advanced models to understand the behavior of atomic nuclei, especially the heaviest and rarest ones. Two scientists, American physicist William Myers and Polish physicist Władysław Świątecki, created a new version of what's called the nuclear shell model. At the same time, German physicist Heiner Meldner, who lived from the year 1939 to 2019, was working independently on a similar idea. This new model paid close attention to the repelling force between positively charged protons known as the Coulomb repulsion. Meldner proposed something unexpected. He suggested that the next magic number for protons, the special number that leads to extra stability in a nucleus, might be 114, not 126, as scientists had previously thought. It was Myers and Świątecki who seemed to have introduced the now famous phrase, island of stability. This term describes a group of very heavy elements that might have unusually long lifespans due to their internal structure. American chemist Glenn Seaborg, who helped discover many of these super-heavy elements, quickly adopted and popularized the term. According to the ideas of Myers and Świątecki, some of these super-heavy atoms could survive longer because they would have high fission barriers, a kind of protection against splitting apart. Their work was expanded further by Soviet physicist Wilhelm Strutinsky, who improved the nuclear shell model by blending it with another approach known as the liquid drop model. This combination became known as the macroscopic-microscopic method. It allowed scientists to make more accurate predictions about which nuclei would be stable. With this new model, Swedish physicist Sven Nilsson and several other research teams carried out detailed calculations and concluded that a specific nucleus, called 298 flerovium, with 114 protons and 184 neutrons, might be especially stable. This challenged an earlier prediction made in 1957, which had suggested that a nucleus with 126 protons and 184 neutrons, known as unbihexium, would be the most stable. Since then, scientists have continued to debate which proton number should be considered magic, with suggestions ranging from 114 to 126. Even now, there is still no agreement on the exact number. Excitement around the idea of this mysterious island of stability grew during the 1960s. Some computer models predicted that atoms in this region might live for billions of years. These elements were expected to resist falling apart, despite being extremely heavy, and might be useful in ways never seen before. For instance, they could serve as neutron sources in particle accelerators, become a part of new kinds of nuclear weapons due to their low critical mass and high neutron output, or even be used as nuclear fuel to power future space missions. These exciting possibilities pushed many scientists in the 1960s and 1970s to go looking for super-heavy elements, both in nature and by trying to create them in laboratories. During the 1970s, many labs around the world conducted experiments to create elements with atomic numbers between 110 and 127. They used a method called fusion-evaporation reactions. In these experiments, a heavy atomic nucleus was bombarded with high-speed particles from a particle accelerator, and the resulting fused nucleus would then release excess energy by evaporating a few particles like protons, neutrons, or helium nuclei, also called alpha particles. There were two types of fusion reactions used: cold fusion, which involved lower energies, and hot fusion, which used higher energies. The results depended heavily on which method was used. For example, scientists hoped that smashing together curium-248 and argon-40 might produce isotopes of element 114, and that thorium-232 with krypton-84 could lead to isotopes of element 126. Unfortunately, none of these early experiments succeeded. Scientists began to suspect that the techniques used might not be sensitive enough, or that the new nuclei created might be so unstable that they decayed before they could even be detected. Later, successful experiments confirmed that the heavier the element, the shorter its life and the harder it was to produce. As of the year 2022, the highest success rate, or cross-section, for creating a super-heavy nucleus close to the island of stability was for element number 115, known as moscovium, created by colliding americium-243 with calcium-48. Scientists also searched for naturally occurring super-heavy elements in rocks and minerals, but those efforts failed too. If such elements exist in nature, they are extremely rare, less than 1 part in 10 quadrillion. Still, scientists didn't give up. Every few years, new super-heavy elements were successfully created in the lab using particle accelerators and refined fusion techniques. In 1969, element 104, Rutherfordium, became the first of the transactinide elements to be discovered. By 1996, scientists had reached element 112, copernicium, just 2 steps away from the predicted magic number of 114. Although these newly created elements lived only for a few seconds, their very existence suggested that something was protecting them from immediate decay. Without this extra stability from closed shells of protons and neutrons, these elements would not exist at all. In 1998, a team of Russian scientists led by Yuri Oganessian at the Joint Institute for Nuclear Research in Dubna managed to create a single atom of flerovium, the element with the predicted magic number of 114. Amazingly, this atom survived for more than 30 seconds, an incredibly long time for such a heavy nucleus. Even more exciting was that it decayed in a predictable way, not by breaking apart, but by releasing alpha particles step by step. This kind of decay was exactly what scientists expected from an element inside the island of stability. Although the exact experiment has not been repeated successfully, and there are still some doubts about that first atom of flerovium, later experiments have confirmed the existence of other superheavy elements all the way up to element 118, arganesson. Interestingly, these newer elements have half-lives longer than first expected, which supports the theory of an island of stability. In 2021, a new study suggested that the extra stability seen near element 114 might not be caused by the number of protons alone. Instead, the neutron count, especially getting close to 184 neutrons, seems to play a larger role. The most neutron-rich superheavy elements confirmed so far, livermorium 293 and tennessine 294, have only 177 neutrons. But the trend is clear. As more neutrons are added, stability increases. One dramatic example is copernicium 285, which has a half-life nearly 100,000 times longer than copernicium 277, thanks to its 8 extra neutrons. This trend suggests that future, heavier isotopes near 184 neutrons might be even more stable. While the most stable nuclei within the island of stability are expected to be nearly spherical, studies beginning in the early 1990s showed that not all super-heavy nuclei are shaped like perfect spheres. Polish physicists Zygmunt Partyk and Adam Sobaczewski were among the first to show that some of these nuclei are actually deformed, more like rugby balls than perfect spheres. These deformed shapes shift the locations of the magic numbers. In the region of elements with atomic numbers between 106 and 108 and neutron counts between 160 and 164, scientists have found that the shell effects can make the nuclei more resistant to splitting apart. These nuclei may only decay by releasing alpha particles, not by breaking in half. One special case is hassium-270, now believed to be a doubly magic deformed nucleus with 108 protons and 162 neutrons. It lives for about 9 seconds, which is long by super-heavy standards. This supports the idea that there's not just one island of stability, but perhaps even a peninsula of relatively stable, deformed, super-heavy nuclei connecting to the main island. This discovery also suggests that the island of stability may not be completely cut off from other, more stable regions. Instead, it could be connected by a narrow bridge of less spherical, but still long-lived nuclei, offering more hope for reaching the very heart of the island someday. Scientists believe there is a mysterious and promising place in the world of atoms called the island of stability. This is a region in the chart of elements where some super-heavy atoms might be more stable and live longer than others. However, no one has yet found or created any of these special atoms that would lie right at the center of this island. Because of this, we still don't know exactly how long they would last. Most scientists think these atoms probably wouldn't last very long, maybe just a few minutes or days. But some calculations suggest that certain atoms on this island could survive for as long as 100 years, or even as long as 1 billion years. A big reason these atoms might be more stable has to do with something called a shell closure. Think of the nucleus of an atom like a crowded dance floor. If the right number of dancers, protons and neutrons, are on the floor, it becomes a very stable arrangement. One of these special numbers is a neutron count of 184. When an atom has that number of neutrons, it may be harder for it to split apart or decay. This effect could slow down dangerous breakdowns like alpha decay or spontaneous fission, which are ways atoms naturally fall apart. For example, atoms around the size of element number 114, with a total mass number of about 298, are predicted to benefit from this shell closure. They may resist breaking apart so strongly that their fission half-lives. How long it takes for half of them to undergo fission could be about 1,000 trillion times longer than atoms without this special stability. That is a number with 30 zeros. However, some super-heavy atoms, like one called flerovium-284, which has only 170 neutrons, are still somewhat stable. This atom breaks apart through fission in just 2.5 thousandths of a second, but that's still longer than expected for something so neutron-deficient. Beyond this point, for atoms with fewer than 170 neutrons, or more than 120 protons, or more than 184 neutrons, things become much more unstable. These atoms might break apart in millionths of a second, or even in times as short as 1/10 billionth of a second if they have no protective fission barriers. In contrast, an atom like flerovium-298, which sits right at the heart of the predicted island of stability, might survive for as long as 10 quintillion years. That is a 1 followed by 19 zeros. But even in this region, atoms are expected to break down either by alpha decay or by fission, and which process wins out depends on the exact structure of the atom. Scientists have tried to calculate how long atoms with between 100 and 130 protons would take to undergo alpha decay. They used a model based on quantum tunneling, a kind of atomic shortcut, and found that the numbers matched real measurements for some of the heaviest atoms we've ever created. Some of the most long-lasting atoms may also be the ones lying on something called the beta stability line. Unlike alpha decay or fission, which involve the atom losing particles and becoming smaller, beta decay is more like the atom rearranging itself slightly. In beta decay, a neutron becomes a proton, or a proton becomes a neutron, helping the atom shift closer to a more stable form without changing its mass. For example, scientists think that atoms like flerovium-291 and nihonium-291 might go through beta decay and slowly slide closer to the center of the island of stability. But there is still a lot of uncertainty. Some similar atoms, like flerovium-290 or moscovium-293, might break apart through alpha decay before beta decay even has a chance. There are many predictions about which atoms in this region might live the longest. Some models suggest that atoms like copernicium-291 and copernicium-293 could last around 100 years. Others think darmstadtium-294 could live for 300 years, or darmstadtium-293 could last as long as 3,500 years. All these atoms sit near that magic neutron number of 184. Interestingly, not all scientists agree on the exact center of the island of stability. Some think the most stable atoms might not be perfectly spherical, but instead slightly squished or stretched, what scientists call nuclear deformation. If so, the true center of the island might be an atom with 122 protons and 184 neutrons, called unbibium-306. This atom might resist fission strongly, but still not live long due to alpha decay. Some researchers also believe that this entire island of stability might not have a sharp peak, but instead be like a coral reef, wide and flat, with many atoms showing a bit more stability, but none standing out as truly immortal. There's another possible way these atoms could break down, something called cluster decay. This is when an atom spits out a small chunk of itself, larger than an alpha particle but smaller than in fission. Romanian and German scientists have suggested that this kind of decay could start to matter more as we look at heavier and heavier elements. Around atomic number 124, cluster decay might even become the main way these atoms fall apart. Even though atoms on the island of stability might live for hundreds or even thousands of years, that is still not nearly long enough for them to have survived on Earth since the planet was formed. Because of this, they are not found in nature today. Also, the atoms between the ones we know, like uranium and thorium, and the island of stability are very unstable, which makes it hard for stars or cosmic events to create stable atoms from this island during nucleosynthesis processes like the R process. Most of the heaviest atoms we know of tend to break down very quickly, usually through spontaneous fission. Sometimes, even when they capture a neutron or go through beta decay, they still end up fissioning almost immediately afterward. This blocks the path toward the island of stability and makes it nearly impossible to produce these long-living atoms in nature. Because of this, we have never seen atoms like hassium-292 or flerovium-298 in nature. Scientists think this is because only a few of them were ever created in the first place, and those that were made didn't live long enough to survive to the present day. Careful studies using very sensitive equipment have searched for them in natural materials and have found that, if they exist at all, they are present in amounts as tiny as 1 part in 100 trillion compared to stable atoms. Still, there is a glimmer of hope. In the year 2013, a group of Russian scientists led by Valery Zagrebaev suggested that some long-living atoms like copernicium might exist in tiny amounts, perhaps 1 part in 1 trillion compared to lead, and might even be detected in cosmic rays. In the same year, another team led by Alexander Bagulya reported what might have been the first glimpse of these elusive atoms. They found signs of 3 possible super-heavy nuclei inside tiny crystals from meteorites. These mysterious atoms seem to have between 105 and 130 protons, and one of them may have had between 113 and 129 protons. The scientists estimated that these atoms might live for at least 3,000 years. Although these results still need to be confirmed by other studies, they provide an exciting hint that the island of stability may truly exist. They also match up well with theoretical predictions about how long such atoms might survive. Scientists have suggested that the unusual presence of short-lived radioactive materials in a strange star called Przybylski's star might be explained by the slow breakdown or decay of very heavy and long-lasting elements. These elements are thought to belong to a mysterious area on the periodic table known as the Island of Stability. This is a theoretical region where super-heavy elements might exist for longer periods of time without breaking apart quickly. Creating these stable, super-heavy elements is extremely difficult. The main problem is that the atoms we can currently use to start the process don't have enough neutrons. Some scientists have proposed using radioactive ion beams like sulfur-44 together with actinide elements such as curium-248. This combination could help create nuclei with more neutrons closer to the center of the island of stability. However, these special radioactive beams are not yet powerful enough for the experiments that would be needed. Still, there may be other heavy isotopes like curium-250 and einsteinium-254 that could be used as targets. These could help produce new isotopes with slightly more neutrons than those we already know. But even making just a few milligrams of these rare materials is incredibly hard, which makes the experiments very challenging. There is also another possible method that involves a reaction called fusion evaporation. This is the same process used in past experiments where calcium-48 was fired at other elements. If scientists tweak the energy levels of these reactions so that fewer neutrons are lost, or if they explore reactions where small charged particles like protons or alpha particles are released along with neutrons, they might be able to create isotopes that are richer in neutrons. These isotopes could belong to elements with atomic numbers between 111 and 117. Although the chances of success, known as cross-sections, are very low, ranging from just 1 to 900 femtobarns, an extremely tiny unit of probability. These reactions might allow researchers to create super-heavy isotopes that have never been seen before. Some of these isotopes, like moscovium-291, flerovium-291, and nihonium-291, might decay slowly by a process called electron capture. In this process, a proton in the nucleus turns into a neutron. Along with alpha decay, this could lead to the formation of nuclei like Copernicium-291, which is believed to lie near the very heart of the island of stability. However, this idea is still just a theory, as no super-heavy elements near the stable zone have been made yet, and predictions about their behavior differ depending on the scientific model used. In the year 2024, researchers at the Joint Institute for Nuclear Research, JINR, in Russia observed a very rare decay path of Moscovium-289. This was seen during a reaction between plutonium-242 and titanium-50, which was aimed at creating new isotopes of the element livermorium. What made this observation special was that it involved a rare type of reaction where charged particles were emitted, something never successfully seen before in a hot fusion experiment involving an actinide target and a projectile with an atomic number of 20 or more. There's another challenge in making super-heavy elements, a process called slow neutron capture, which can make elements as heavy as fermium-257, gets interrupted by unstable fermium isotopes like fermium-258. This isotope breaks apart almost instantly within about 370 microseconds in a process called spontaneous fission. Scientists call this obstacle the fermium gap, and it blocks the path to heavier elements. One wild idea to get past this gap is to use nuclear explosions, controlled ones, of course, with neutron levels 1,000 times higher than what we get in today's nuclear reactors. This would mimic a natural process in space called the R process, which builds up heavy elements in exploding stars. A scientist named Meldner first proposed this concept back in the year 1972. If it works, it might allow for the creation of larger amounts of super-heavy elements within the island of stability. However, the exact role of fission in these reactions is not well understood and could affect how much of the super-heavy material is actually produced. There's another promising approach, using multinucleon transfer reactions. This involves smashing two heavy atomic nuclei like uranium-238 and curium-248 together at low speeds. Sometimes, instead of completely merging or just bouncing off, the two atoms trade pieces of their nuclei. This process, called inverse quasifission, could lead to the formation of very neutron-rich elements, including the predicted but never observed flerovium-298. If the stabilizing shell effects around atomic number 114 are strong enough, this method might work. That said, lighter elements like nobelium and seaborgium, which have atomic numbers between 102 and 106, seem to form more easily in these reactions. Initial experiments using uranium-uranium and uranium-curium collisions haven't yet created anything heavier than mendelevium, which has an atomic number of 101. However, the uranium-curium combination did give better results, hinting that using even heavier targets, like Einsteinium-254, might lead to the creation of true super-heavy elements. Later studies supported this idea, suggesting that reactions using these heavier targets could produce elements with atomic numbers up to 109. In the year 2018, a team led by Sarah Winchell at the Texas A&M Cyclotron Institute studied a reaction between uranium-238 and thorium-232. They observed several mysterious alpha decays that might belong to completely new, super-heavy isotopes with atomic numbers somewhere between 104 and 116. But more work is needed to confirm exactly what these products are. These results suggest that the forces holding the nucleus together, especially shell effects, play a huge role in whether these reactions succeed, and that the island of stability might indeed be within reach using these methods. Interestingly, scientists also think there could be other islands of stability even beyond the main one. For example, one is expected near element 126 with 308 neutrons, and another even heavier region might contain elements like 472, 164, or 482, 164, with up to 318 neutrons. These hypothetical super-heavy elements could be very resistant to breaking apart and might even last for years before decaying. That would make them surprisingly stable compared to other radioactive elements. There may also be smaller, safe zones of stability near other predicted shell closures, like element 126 with 342 nucleons, or element 154 with 462 nucleons. But the more protons an element has, the harder it becomes to keep the nucleus from falling apart due to the growing repulsion between the positively charged protons. This could mean that these stable regions are isolated islands surrounded by a sea of instability where other super-heavy atoms break apart so quickly that they don't really exist at all. Even more fascinating is a bold theory about what lies beyond atomic mass 300. Scientists have imagined an entire continent of stability made of something completely different. A strange kind of matter made not of regular protons and neutrons, but of free-floating up and down quarks. This type of matter, called stable quark matter, might be even more tightly bound than normal nuclear matter. If it exists, heavy atomic nuclei might eventually decay into it once they get large enough. Some scientists think it might be possible to create this exotic matter in the same kinds of fusion reactions used to make normal super-heavy elements. If real, this quark matter could be incredibly stable and immune to fission because of how tightly its parts stick together.